What if everything we've ever seen, every star, every galaxy, every shimmering cosmic wonder, is just a sliver of what's truly out there? For centuries, humanity has gazed up at the night sky and believed we were beginning to understand the universe. But what if we've only been scratching the surface? The truth is, the cosmos holds secrets far deeper and stranger than we ever imagined. In fact, nearly everything we thought we knew about the universe might only be a fraction of the full story. What we see, what we can touch, what we can measure, all of it makes up less than 5% of existence. The rest is hidden in plain sight, yet completely invisible to our eyes and our finest instruments. This isn't science fiction. This is the frontier of modern cosmology. Welcome to the greatest detective story in all of science, the search for dark matter and dark energy. These two mysteries represent the most profound puzzles ever encountered in our quest to understand reality. Think of them as the universe's best-kept secrets, cosmic enigmas that have stubbornly resisted all our efforts to unveil them. Dark matter, an invisible substance that tugs on galaxies and shapes the cosmos, yet emits no light and slips through our detectors unnoticed. Dark energy, a mysterious force pushing the universe apart faster and faster, defying gravity and confusing even our brightest minds. Together, they make up 95% of everything that exists, and yet we can't see them, we can't touch them, and we still don't truly know what they are. That's what we're diving into today, a journey to the edges of understanding, where the known rules of physics begin to fray and the real magic of the cosmos reveals itself. This isn't just a story about distant stars and far-off galaxies. It's about us, our curiosity, our determination, and our unending desire to solve the universe's greatest riddles. You're about to explore how scientists are piecing together clues from the farthest reaches of space and time, using ingenuity and imagination to shed light on the darkness. So settle in, open your mind, and get ready to see the universe in a whole new way, because what comes next might just change how you see everything. Our story begins not in the modern era of powerful telescopes and space probes, but nearly a century ago, with a brilliant and often overlooked astronomer named Fritz Zwicky. While studying the Coma Cluster, a massive gathering of galaxies millions of light-years away, Zwicky noticed something that simply didn't add up. He measured how fast these galaxies were whipping around their common center of gravity, and the speeds were staggering, so fast, in fact, that the entire cluster should have flown apart. The gravitational glue provided by all the stars, gas, and dust we could see was nowhere near strong enough to hold these galaxies together. It was like watching cars on a racetrack moving at impossible speeds without any friction to keep them on the curve. Zwicky, in a flash of insight, proposed there must be some unseen matter providing the extra gravity, a hidden mass he called dunkel materie, or dark matter. At the time, his idea was so radical that many in the scientific community dismissed it outright, chalking it up to a measurement error or an overactive imagination. The case for this cosmic missing mass might have remained a curious footnote for decades, if not for the meticulous work of another visionary astronomer, Vera Rubin, in the 1970s. While studying the rotation of individual spiral galaxies, Rubin and her colleague Kent Ford made an even more startling discovery. According to the well-established laws of gravity, stars on the outer edges of a galaxy should orbit much more slowly than those near the bright, dense center, just as Pluto, in our own solar system, moves far more sluggishly around the Sun than Mercury does. But their data revealed no such slowdown. Stars at the very fringes of galaxies were racing around at nearly the same incredible speed as those close to the core. This wasn't just true for one or two galaxies, it was a universal pattern. The only logical conclusion was that each galaxy was enveloped in an enormous, massive halo of something invisible, a halo that provided the extra gravitational pull to keep those far-flung stars from flying off into the void. Rubin's galaxy rotation curves became the most compelling evidence yet that Zwicky's dark matter was not only real but everywhere. Since then, the evidence has only continued to mount, converging from completely different corners of astronomy to tell the same astonishing story. When we observe massive clusters of galaxies, we can see how their immense gravity bends the light from more distant objects behind them, an effect called gravitational lensing. The amount of bending we see tells us how much mass is in the cluster, and time after time, the calculated mass is far greater than the sum of all the visible parts. Furthermore, when we look at the large-scale structure of the universe, the vast cosmic web of filaments and voids that galaxies are arranged along the patterns only make sense if we include a scaffolding of dark matter. Ordinary matter alone simply doesn't have enough gravitational oomph to pull together such immense structures in the age of the universe. The verdict from every line of inquiry is unanimous and staggering. What we see and know is the exception, not the rule. For every ounce of atoms that makes up our world, our bodies, and our stars, there is 5 times more mass out there in the form of this mysterious, invisible substance. So if we can't see dark matter and it doesn't interact with light, how do we know it's really there? The answer lies in one of the most elegant predictions ever made in science, a concept so strange that even its originator had doubts. Albert Einstein's theory of general relativity proposed that gravity isn't just a force between masses, but a warping of the very fabric of space and time. A massive object like a star or a galaxy creates a sort of dent in this cosmic fabric, and this curvature dictates how other objects move. But Einstein took it a step further, predicting that even light itself, traveling in a straight line, would have its path bent as it passed through one of these gravitational dents. It's as if space itself is a distorted lens, and light has no choice but to follow the curves. This phenomenon, called gravitational lensing, transforms entire galaxy clusters into the universe's most powerful natural telescopes. Imagine you're looking at a distant, faint galaxy through a perfectly shaped wine glass. The curved glass distorts and magnifies the image, creating strange, stretched arcs of light. This is precisely what happens on a cosmic scale. When light from a faraway galaxy travels toward us and passes through or near a massive galaxy cluster, the incredible gravity of that cluster, mostly provided by its immense halo of dark matter, bends the light rays. From our perspective, that distant galaxy's image can be stretched, magnified, duplicated into multiple images, or twisted into brilliant, shimmering arcs of light that ring the foreground cluster. By meticulously mapping these distortions, astronomers can essentially reverse engineer the scene. They can calculate exactly how much mass must be present in the foreground cluster to cause the observed bending, creating a detailed map of all the mass, both seen and unseen. Perhaps the most stunning and conclusive example of this is a system known as the bullet cluster. This isn't a single galaxy, but 2 enormous clusters of galaxies that have recently collided with each other at unimaginable speeds. This cosmic crash provided a perfect natural experiment. During such a collision, the different components of the clusters behave in very different ways. The vast clouds of hot gas, the normal, visible matter that glows in X-rays, smash into each other, much like 2 clouds of smoke colliding. This gas slows down and gets stuck in the middle of the collision. But the dark matter and the individual galaxies, which are mostly empty space, don't interact in this way. They simply pass right through one another without slowing down. When astronomers observed the bullet cluster, they saw exactly this separation. The pink glow of the hot, X-ray emitting gas was located right in the center of the collision, where it had been slowed by the impact. But when they used gravitational lensing to map the total mass, the true gravitational bulk of the clusters was not in the center with the gas. It had sailed far ahead, coinciding perfectly with the positions of the visible galaxies. This was a direct, observational proof that most of the mass is something completely separate from the normal matter we can see. It doesn't interact with anything except through gravity. The bullet cluster wasn't just suggesting dark matter exists. It was showing us its behavior, demonstrating its ghostly nature in a way that is almost impossible to refute. It's a cosmic fingerprint left at the scene of a collision, pointing squarely at an invisible culprit. These gravitational lensing maps provide undeniable, indirect proof of dark matter's presence, but to truly understand its fundamental nature, we have to look even further back in time, all the way back to the very beginning. The story of dark matter isn't just written in the movements of modern galaxies. It's imprinted on the oldest light in the universe, a fossilized echo from the moment the cosmos first became transparent. This ancient light is called the cosmic microwave background, and it is our single most important window into the infancy of everything. It's the faded afterglow of the Big Bang itself, a snapshot of the universe when it was a mere 380,000 years old, a cosmic baby picture. Before this time, the universe was an opaque, searing hot soup of particles and energy, so dense that light couldn't travel any meaningful distance before bouncing off an electron. It was a chaotic, swirling fog, but as the universe expanded and cooled, electrons and protons finally combined to form the first stable hydrogen atoms in an event known as recombination. Suddenly, the fog cleared. Light, which had been trapped, was finally set free to travel across the cosmos. That first burst of light has been stretching with the expansion of the universe for over 13 billion years, cooling all the way down to just a few degrees above absolute zero. Today, it fills every cubic inch of space as a faint microwave static, a cold whisper of that initial hot burst. This background radiation is not perfectly smooth. If it were, it would tell a very simple story. Instead, it is filled with tiny, microscopic variations in temperature, tiny ripples of slightly hotter and slightly colder patches. These ripples are incredibly important. They represent the seeds of all future structure in the universe. They are the faint imprints of the first tiny gravitational over densities, the places where matter was ever so slightly more packed together. Over billions of years, gravity would amplify these tiny fluctuations, pulling more and more matter into these dense spots, eventually building the magnificent galaxies and clusters we see today. But the critical question is, what kind of matter provided the primary gravitational anchor for these seeds to grow? This is where dark matter proves its indispensable role. Ordinary matter, the atoms that make up everything we see, had a major problem in the early universe. It was under immense pressure from the intense radiation that filled space. This radiation pressure created powerful sound waves that pushed against the clumping of normal matter, effectively ironing out any small wrinkles and preventing it from collapsing efficiently under its own gravity. It was like trying to build a sandcastle with waves constantly washing over it. Dark matter, however, is completely different because it doesn't interact with light or radiation at all. It was completely immune to this pressure. It felt gravity and gravity alone. This meant that dark matter could start clumping together immediately after the Big Bang, long before ordinary matter could. It formed a vast, invisible gravitational scaffold, a cosmic skeleton upon which normal matter could later accumulate. The precise pattern of hot and cold spots in the cosmic microwave background is a detailed record of these first gravitational interactions. Missions like the European Space Agency's Planck satellite have mapped this afterglow with breathtaking precision, measuring these temperature differences down to a few millionths of a degree. The pattern they see is a perfect match for a universe where the initial gravitational wells that created the temperature ripples were primarily carved out by dark matter. The size, distribution, and intensity of these fluctuations tell us with remarkable accuracy exactly how much dark matter there must be. The calculations are unequivocal. Dark matter makes up about 27% of the total energy and content of the universe. Compared to the paltry 5% that is all the stars, planets, gas, and dust we call ordinary matter, the message is clear. we are not just the minority, we are the rare, visible decoration on a massive, hidden framework of dark matter that dictated the destiny of the cosmos from its very first moments. But if dark matter was so essential in building the universe's largest structures, how did it help with the smaller ones, like the very first galaxies? This brings us to one of the most profound puzzles in modern cosmology, a challenge so significant it's known as the galaxy formation paradox. The issue is one of time. Based on our understanding of gravity and the initial conditions seen in the cosmic microwave background, there simply hasn't been enough time since the Big Bang for galaxies to form through the gravitational collapse of ordinary matter alone. The radiant pressure in the early universe, as we discussed, prevented atoms from clumping together effectively. If normal matter had to do all the work by itself, our cosmos would still be a vast, featureless sea of hydrogen gas, with perhaps a few tiny, faint protogalaxies just starting to coalesce. Yet, we observe a universe teeming with magnificent, fully formed galaxies that emerged when the cosmos was just a fraction of its current age. The resolution to this paradox lies in the unique properties of dark matter. While ordinary matter was struggling against the intense radiation pressure, dark matter was quietly and efficiently getting down to business. Unaffected by the push and shove of light, it began collapsing under its own gravity immediately after the Big Bang, forming vast, intricate structures. The most powerful tool we have for visualizing this process isn't a telescope, but a supercomputer. Cosmologists run incredibly sophisticated simulations that model the evolution of the universe from its first moments to the present day. When these simulations only include the gravitational influence of normal atoms, they produce a universe that looks nothing like our own. It's far too smooth and undeveloped. But when they add the correct amount of dark matter, something magical happens. The simulations reveal a cosmic dance of incredible beauty and complexity. Dark matter, drawn by gravity, first forms a gigantic web-like structure, a cosmic skeleton of dense knots connected by long, thin filaments with enormous voids in between. This is the famous cosmic web. Within this web, the densest knots of dark matter collapse further to form what are known as dark matter halos, roughly spherical, incredibly massive clouds of this invisible substance. These halos are the universe's ultimate gravitational anchors. Their immense gravity creates deep wells in the fabric of space-time. It is into these pre-existing wells that the ordinary matter, the hydrogen and helium gas, can later flow. Once the universe had expanded and cooled enough for radiation pressure to weaken, this gas was already perfectly positioned. It simply fell into the gravitational wells prepared by the dark matter, collapsing quickly and efficiently to form the first dense clouds that would ignite as the very first stars and the seeds of the very first galaxies. This dark matter scaffolding didn't just make galaxy formation possible, it made it incredibly efficient and surprisingly fast. The halos acted as ready-made templates, dictating where galaxies would form, how massive they would become, and even how they would be distributed in space. Without this invisible framework guiding the process, the majestic spiral and elliptical galaxies we see today, including our own Milky Way, could never have assembled themselves in the 13.8 billion years the universe has existed. The sheer speed and scale of galaxy formation is one of the most compelling pieces of evidence that dark matter is not just real, but was the master architect of the cosmic structures we take for granted. So if dark matter built the cosmic web and sculpted the galaxies, what exactly is it made of? This question has launched one of the most ambitious and technologically stunning quests in modern science: the direct search for the dark matter particle itself. For decades, the most promising candidate has been a hypothetical entity known as a WIMP, which stands for Weakly Interacting Massive Particle. The name itself perfectly captures its elusive nature. The idea is that these particles have mass, which is how they exert gravity, but their interactions with normal matter are extraordinarily feeble. happening only through the weak nuclear force and gravity. This would explain why trillions of these particles could be streaming through your body every second without you ever noticing a thing. The strategy for catching one of these ghostly particles is a masterpiece of scientific ingenuity. Because these interactions would be so incredibly rare, physicists had to design experiments of immense sensitivity, and they had to hide them from the constant barrage of cosmic radiation and other background noise that would easily swamp any potential dark matter signal. The solution was to go deep, building enormous, hypersensitive detectors in abandoned mines, tunnels under mountains, or deep underground laboratories. Places like the Sanford Underground Research Facility in South Dakota, over a mile beneath the surface, use a massive amount of rock as a natural shield, filtering out the distracting cosmic chatter from the surface. At the heart of these labs are the detectors themselves, technological marvels like Xenon 1T and its successor Xeno NNT, Lux, and Panda X. These are not simple machines, they are ultra-pure vats of liquid xenon, chilled to extremely low temperatures and watched over by arrays of exquisitely sensitive light sensors. The principle is to wait with immense patience for the once-in-a-lifetime event where a passing WIMP might actually bump into the nucleus of a xenon atom. That tiny transfer of energy would create a faint flash of light and free some electrons, a dual signal that the detectors are designed to pick up. It's the scientific equivalent of trying to hear a single, specific pin drop in a bustling city during a thunderstorm by isolating the most silent room on Earth and listening for years on end. The profound mystery we face today is that despite decades of operation and these detectors becoming exponentially more sensitive, they have consistently found nothing. The expected WIMP signal has stubbornly refused to appear. Each new generation of experiment, orders of magnitude more powerful than the last, was built with the hope that it would finally be the one to make the historic discovery. Instead, they have mostly returned empty results, quietly ruling out vast swaths of possible masses and interaction strengths for WIMP particles. This ongoing null result is in its own way one of the most significant findings in particle physics. It is forcing a monumental rethink of the leading theory and opening the door to a whole zoo of other, even more exotic possibilities for what dark matter could be. With the persistent silence from WIMP detectors growing louder, scientists have been forced to broaden their search, turning to a radically different and wonderfully elegant candidate known as the axion. This idea didn't even originate from cosmology. It was born from a deep and perplexing mystery in the world of quantum physics. Theorists were trying to understand why the strong nuclear force, which glues protons and neutrons together inside an atom's nucleus, seems to play by such perfectly symmetrical rules. According to our best models, this force should actually violate a symmetry known as CP, which would have observable and dramatic effects in the universe, effects we simply do not see. This glaring theoretical problem is called the strong CP problem. To resolve it, physicists Roberto Pexi and Helen Quinn proposed a clever new symmetry, and shortly after, Frank Wilczek and Steven Weinberg realized this solution would inevitably produce a new, very light, very weakly interacting particle. Wilczek named it the axion after a brand of laundry detergent because it was theorized to clean up this messy problem in particle physics. While born to solve one puzzle, the axion soon revealed itself as a perfect contender for another. If they exist, axions would have been produced in colossal numbers in the searing heat of the Big Bang, and their properties align beautifully with what we require for dark matter. They would be shockingly light, potentially billions of times less massive than an electron, but they would make up for their lack of individual heft with their unimaginable abundance. Think of it like this: if WIMP were the strategy of finding a few massive boulders in a dark field, the axion approach is to look for a universe-filling fog of trillions upon trillions of specks of dust in every cubic inch of space. Their collective gravitational pull would be immense, weaving the cosmic web just as effectively as any other form of dark matter. Their ghostly nature is even more extreme than that of WIMP. Axions wouldn't interact via the weak nuclear force at all. Instead, in the presence of strong magnetic fields, they are predicted to exhibit a strange and useful quirk. They can spontaneously convert into particles of light or photons. This unique signature is the key to hunting them. It has inspired a new generation of experiments that are less like underground particle catchers and more like incredibly sensitive cosmic radios, all tuned to search for one specific, faint station broadcast by the universe itself. The most promising technique is to use a powerful magnet to create the conditions for this conversion. Inside a strong magnetic field, an axion passing through might transform into a microwave photon. The frequency or pitch of this photon is directly tied to the axion's mass. The challenge is that we don't know the exact mass, so we have to scan through millions of possible frequencies, listening patiently for a faint signal rising above the background noise. Experiments like the Axion Dark Matter E-experiment, or ADMX, based at the University of Washington, are doing exactly this. The heart of ADMX is a resonant cavity, essentially a sophisticated metal can placed inside a powerful magnet and cooled to near absolute zero to suppress thermal noise. The cavity can be tuned like adjusting the dial on an old radio, and if an axion with the right mass is present, the experiment should hear a faint but telltale whisper of microwaves as the particle converts inside the magnetic field. This shift from massive vats of xenon to ultra-sensitive microwave receivers represents a profound pivot in the dark matter quest. It's a move from brute force detection of rare nuclear collisions to the delicate art of quantum eavesdropping on the cosmos. The axion hypothesis turns the entire galaxy into a potential source of signal, as the halo of dark matter surrounding our Milky Way should be raining these particles down on us continuously. While no definitive signal has been found yet, the search is accelerating with new international collaborations and next-generation experiments like MADMAX in Germany, planning to use intricate arrays of disks to amplify the signal over a wider range of masses. The pursuit of the axion is a beautiful example of scientific convergence, where a solution to one deep puzzle in theoretical physics may also hold the key to unlocking the greatest mystery in all of cosmology. Yet the persistent failure to find these particles has led some scientists to propose a radically different solution, one so bold it challenges the very foundations of physics. What if we've been chasing a ghost because we've misdiagnosed the problem entirely? What if dark matter doesn't exist and the real issue lies not with an invisible substance, but with our fundamental understanding of gravity itself? This is the core of a profound and ongoing scientific controversy centered on a theory known as modified Newtonian dynamics, or MOND. Its premise is as simple as it is revolutionary. Instead of inventing a new, invisible form of matter to explain the cosmic missing mass, perhaps we just need to tweak the laws of gravity, specifically in realms where gravity is incredibly weak. The story of MOND begins with Israeli physicist Mordechai Milgrom in the early 1980s. He was deeply intrigued by the galaxy rotation curve problem, the puzzling observation that stars orbit galaxies at constant speeds regardless of their distance from the center, defying Newton's laws. Rather than accepting the need for dark matter, Milgrom asked a different question. What if Newton's second law of motion, F equals ma, behaves differently when the acceleration involved becomes extremely tiny? He proposed a new constant, a0, a very low acceleration threshold. Above this threshold, physics operates as Newton and Einstein described, but below it, in the extremely weak gravitational fields found at the edges of galaxies, the force of gravity would effectively become stronger than the standard laws predict. This simple modification produces a startling result. It perfectly flattens galaxy rotation curves, matching the observed data without requiring a single particle of dark matter. The elegance of this idea is deeply appealing. With one simple adjustment, it solves the problem that launched the dark matter hunt. MOND doesn't just fit the data. For individual galaxies, it often makes more accurate predictions than the standard dark matter model. It's a parsimonious solution, appealing to the scientific principle known as Occam's razor, the idea that the simplest explanation, the one that requires the fewest new assumptions, is often the best. Why invent an entire universe of unknown particles when a minor modification to a well-established law could do the trick? However, the universe is rarely so simple, and most of the scientific community remains deeply skeptical of MOND. The theory's greatest strength is also its most significant weakness. It was specifically designed to fix the galaxy rotation problem, but the evidence for dark matter doesn't come from galaxies alone. It comes from multiple, independent lines of inquiry that paint a consistent picture across the entire cosmos. When tested against this broader evidence, MOND begins to falter. Take the bullet cluster, for example. This system provides a direct visual map of where the mass is located, and it clearly shows that the majority of the mass, the stuff causing the gravitational lensing, is separated from the normal matter. MOND, which attributes the extra gravity to a modification of the laws of physics acting on the visible mass, has a very difficult time explaining how the gravitational effect could be completely divorced from the visible material itself. It's a direct hit that the theory has struggled to convincingly counter. The challenges for MOND become even greater when we look at the largest scales in the universe. The cosmic microwave background, that pristine snapshot of the infant universe, shows a very specific pattern of temperature fluctuations. This pattern is a precise reflection of how matter was distributed and interacting just moments after the Big Bang. The standard model of cosmology, which includes dark matter, can use these measurements to predict the exact proportions of dark matter, dark energy, and ordinary matter with incredible accuracy. The resulting model then successfully predicts how the universe will evolve, forming the exact large-scale structure we see today. MOND, in its original form, has no such predictive power for the early universe. It cannot naturally reproduce the detailed power spectrum of the CMB. While some proponents have developed more complex relativistic extensions to MOND to try and address this, these models often have to incorporate their own forms of hidden matter or fields, arguably defeating the original elegant purpose of avoiding unseen components. This is the heart of the great controversy. The standard dark matter model, for all its current frustrations, provides a single, unified framework that explains a breathtakingly diverse set of observations, from the motions of stars within galaxies, to the collisions of galaxy clusters, to the seeds of structure in the early universe. It is a robust, if incomplete, theory. MOND, by contrast, is a brilliant solution to one specific problem, but it has yet to be successfully integrated into a complete cosmological theory that can explain all the evidence without resorting to additional ad hoc assumptions. The debate between these two paradigms is a fantastic example of science in action, a vigorous, sometimes heated, competition of ideas where evidence is the ultimate judge. For now, the weight of that evidence still leans heavily toward the existence of a dark, unseen form of matter, but the persistence of MOND serves as a crucial reminder that our understanding of gravity, one of the most familiar forces in the universe, might still hold surprises. Even with its ghostly nature, dark matter is far from featureless. It doesn't simply form a smooth, uniform fog throughout the cosmos. Instead, it weaves the universe's largest and most intricate structure, a vast, invisible network known as the cosmic web. This web is the true backbone of the universe, a scaffolding of dark matter filaments that stretches across billions of light years, connecting massive galaxy clusters at its densest nodes and leaving enormous, empty voids in between. The galaxies we see are merely the visible traces of this underlying architecture, like glitter sprinkled onto the sticky strands of a spider's web, revealing its shape but not the web itself. To understand how this complex structure emerges, we have to turn to some of the most computationally demanding simulations ever run. Cosmologists use the laws of physics and the initial conditions from the cosmic microwave background to create virtual universes inside supercomputers. These simulations model how dark matter, under the relentless pull of its own gravity, evolves over billions of years. The results are nothing short of breathtaking. They show a dynamic, evolving dance where tiny density fluctuations in the early universe are amplified over eons. Dark matter flows into denser and denser regions, collapsing first into flat sheets, then into long, thin filaments, and finally knotting together at the intersections. These knots become the massive halos that will eventually host entire clusters of galaxies. The final product is an intricate, three-dimensional lattice that matches the large-scale structure we observe with our telescopes almost perfectly. But the predictions from these simulations get even more detailed. They don't just forecast a smooth web, they predict a hierarchy of structure within structure. Within the halo of a single large galaxy like our Milky Way, the simulations suggest there should be hundreds, even thousands, of smaller subhalos, lumps of dark matter that never fully collapsed into their own galaxies. These are the failed galaxies, the dark matter clumps that didn't attract enough ordinary gas to ignite with stars. According to the models, our galaxy should be swarming with these invisible, planet-sized ghosts, each one a dense knot of pure dark matter orbiting within the vast larger halo. This is where we encounter a profound and lingering mystery, one known as the missing satellites problem. When astronomers went looking for the visible counterparts to these predicted subhalos, the small, faint dwarf galaxies that should be lit up by the sparse stars within them, they found a glaring discrepancy. The number of tiny, observed satellite galaxies around the Milky Way is a mere fraction of what the most sophisticated dark matter simulations predict. It's as if our census of a city's population found all the major districts but was missing nearly 90% of the neighborhoods. The simulations say there should be hundreds of these dark clumps, but our telescopes only see a few dozen that have managed to form stars. So where did all the others go? This puzzle has forced scientists to re-examine their assumptions from multiple angles. One compelling possibility is that our understanding of how stars form in the smallest, most pristine environments is incomplete. Perhaps the process of star formation in these tiny dark matter clumps is incredibly inefficient. Maybe the intense ultraviolet radiation from the first massive stars, or even supernova explosions in the early universe, blasted away the gas from these small subhalos before stars could ever get a chance to form, leaving them completely dark and invisible to our telescopes. Another fascinating line of inquiry suggests our models of dark matter itself might need a tweak. The standard, cold, dark matter model assumes the particles move relatively slowly. But what if some dark matter is slightly warmer, moving with more speed? These faster-moving particles would have difficulty clumping together on the very smallest scales, potentially erasing the tiniest subhalos and bringing the simulations into much closer alignment with what we actually see in the sky. The missing satellites problem is no longer seen as a fatal flaw for dark matter, but rather a crucial clue, a cosmic breadcrumb trail that is guiding physicists toward a deeper and more nuanced understanding of how the invisible universe truly operates. For nearly 70 years, the discovery of the universe's expansion had been the cornerstone of modern cosmology. Since Edwin Hubble's groundbreaking observations in the 1920s, scientists had universally accepted one fundamental truth: the cosmic explosion of the Big Bang was gradually slowing down. The entire mass of the cosmos, every galaxy, every star, every particle exerts a gravitational pull on everything else. It was the most natural assumption in the world that this collective gravity would act as a brake, relentlessly tugging at the fabric of space to slow the expansion. The only real question was whether there was enough matter to eventually halt the expansion entirely, leading to a big crunch, or if the universe would simply coast forever towards a cold and quiet end. This was the paradigm, the unshakable foundation upon which decades of cosmological research was built. Everything was about measuring the deceleration. To measure this cosmic slowdown, two brilliant teams of astronomers devised an ambitious plan in the 1990s. They would use the most powerful telescopes on Earth and eventually in space to hunt for a very specific kind of stellar explosion, a Type 1a supernova. These aren't just any exploding stars, they are nature's most perfect standard candles. They occur in a binary star system where a dense white dwarf siphons material from its companion. Once it reaches a critical mass of exactly 1.4 times that of our Sun, it triggers a runaway thermonuclear explosion. Because the trigger mass is always the same, the intrinsic brightness of every Type 1a supernova is nearly identical. This means if you see one that appears faint, you know it must be very far away. If you see one that appears bright, it's relatively close. By meticulously measuring how bright these supernovae appear from Earth and comparing that to their known true brightness, astronomers can calculate their distance with incredible precision. Furthermore, by analyzing the light from these explosions, they can measure how much the universe has stretched since the moment the light was emitted, what scientists call the redshift. The goal for both teams, the Supernova Cosmology project led by Saul Perlmutter and the High Z Supernova Search team led by Brian Schmidt and Adam Rees, was to find these supernovae at truly immense distances, looking back billions of years into the past. By comparing the expansion rate of the universe then to the expansion rate now, they could finally measure the rate of the deceleration. It was a painstaking, grueling process. They would scan large patches of the sky, then return to the same patches nights later to look for new pinpricks of light that hadn't been there before, the telltale sign of a supernova flaring into existence. They had to move fast, obtaining detailed spectra of these faint, fleeting objects before they vanished. They were gathering the most crucial data points in cosmology. As the data began to pour in, a profound unease started to grow within both teams. They were expecting to see that the most distant supernova, the ones that exploded when the universe was much younger, would appear brighter than expected. The logic was that if the expansion was slowing down, the universe was expanding more rapidly in the past than we would predict in a coasting universe. This would mean that a supernova from that early, faster expanding era would be physically closer to us than we thought, and therefore appear brighter. But that's not what the data showed. Instead, the most distant supernovae were fainter, much fainter. Their light had been stretched, dimmed, and diluted more than anyone had anticipated. The only possible explanation was that these supernovae were even farther away than anyone had calculated. And the only way that could be true is if the expansion of the universe was not slowing down at all. It was speeding up. The realization hit each team separately, and it was met with a combination of sheer disbelief and intense skepticism. Scientists are trained to doubt, to assume there must be an error in their methodology, their instruments, or their analysis. Both groups spent months frantically searching for a mistake. Could it be interstellar dust dimming the light? They checked and ruled it out. Could the supernova themselves be intrinsically different billions of years ago? The evidence suggested they were the same. One by one, every conceivable alternative explanation was systematically eliminated. The data was stubborn and unambiguous. The universe's expansion was accelerating. It was as if you tossed a ball into the air, and instead of slowing down as it ascended and falling back to Earth, it shot away from you faster and faster into the sky, defying gravity itself. Something was actively pushing the galaxies apart. This something needed a name. In a nod to the existing cosmic mystery of dark matter, this mysterious repulsive force was dubbed dark energy. The term captured its utterly unknown nature while acknowledging its dominant role in the cosmos. The 1998 announcement of this discovery sent shockwaves through the scientific community, completely upending our understanding of cosmic evolution. It was a paradigm shift of the highest order, so revolutionary that it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. The comfortable assumption of a slowing expansion was gone, replaced by a far more puzzling and dramatic reality. The universe is not only expanding, but it is doing so at an ever-increasing rate, driven by a force that remains to this day the most profound enigma in all of science. This astonishing discovery of an accelerating universe immediately sent physicists scrambling back through their textbooks, searching for any possible explanation within the known laws of physics. And their search led them directly to a concept that had been sitting on the shelf for decades, an idea that its own creator had famously dismissed as his greatest blunder. The story of the cosmological constant is one of the most fascinating tales of scientific hubris, regret, and ultimately, breathtaking vindication. When Albert Einstein was developing his theory of general relativity in 1917, the prevailing scientific belief was that the universe was static, eternal, and unchanging. This was the universe of Newton and Kepler, a fixed, stable cosmic stage. But Einstein's own elegant equations told a very different story. They described a dynamic universe that should either be expanding or contracting under the relentless pull of gravity. A static universe, according to his math, was unstable and should inevitably collapse in on itself. Unwilling to challenge the established view of a steady-state cosmos, Einstein did something that to him felt like a necessary fudge. He introduced an extra term into his equations, a repulsive force he called the cosmological constant, represented by the Greek letter lambda. This wasn't a particle or a substance, it was a property of space itself, an inherent energy woven into the very fabric of the vacuum that would exert a gentle outward pressure, perfectly counterbalancing the inward pull of gravity to keep the universe forever static. Just over a decade later, Edwin Hubble's observations of receding galaxies provided irrefutable evidence that the universe was not static at all, but expanding. Einstein famously traveled to Mount Wilson to see the evidence for himself, and upon seeing Hubble's data, he immediately realized his mistake. He had missed a monumental prediction of his own theory. He discarded the cosmological constant, calling it superfluous, and in later years his greatest blunder. For the better part of a century, that's where the story ended, a curious footnote in the history of a genius's rare era. But the universe, it seems, has a profound sense of irony. The discovery of dark energy in 1998 didn't just revolutionize cosmology, it resurrected Einstein's discarded idea from the grave. The observed acceleration of the universe's expansion fit perfectly with the mathematical description of a positive cosmological constant. That repulsive force he had invented to hold the universe still was in fact the very thing that was now pushing it apart faster and faster. In a stunning twist of fate, Einstein's so-called blunder was not a mistake at all, but a prediction decades ahead of its time. His cosmological constant is now the simplest and most popular explanation for dark energy, a uniform energy inherent to empty space itself, driving the accelerated expansion we observe today. This elegant solution, however, comes with a catastrophic problem, one that exposes a fundamental rift between our two most successful theories of reality. To understand why, we have to venture into the bizarre world of quantum mechanics. Quantum field theory tells us that what we perceive as a perfect vacuum, complete and utter emptiness, is nothing of the sort. At the tiniest scales, the vacuum is a seething, bubbling foam of virtual particles. Pairs of particles and antiparticles are constantly flickering into and out of existence, borrowing energy from the vacuum for an unimaginably short time before annihilating and paying the energy back. This perpetual, energetic dance is not just theoretical. We can measure its effects in the lab through phenomena like the Casimir effect. All this frantic activity should endow every cubic centimeter of empty space with a certain amount of energy, a vacuum energy. And according to the rules of quantum field theory, This vacuum energy should behave in exactly the same way as Einstein's cosmological constant, exerting a repulsive gravitational effect. This is where we arrive at the single most embarrassing numerical discrepancy in the entire history of science. Physicists can calculate how much energy this quantum vacuum foam should have. It's a calculation based on well-tested physics. Meanwhile, cosmologists can observe how much repulsive energy is actually out there, driving the acceleration of the universe by measuring the rate of expansion with supernova and the cosmic microwave background. These two numbers, one from the world of the very small and one from the world of the very large, should be the same, but they are not even close. The value predicted by quantum physics is larger than the value observed by astronomers by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. To try and comprehend the sheer scale of this error, imagine an estimate for the width of the entire observable universe that was off by the width of a single atom. This discrepancy is billions upon billions of times worse than that. It is, by any measure, the worst theoretical prediction ever made. This colossal failure is known as the cosmological constant problem, and it represents a glaring warning sign that there is a deep, fundamental piece of physics that we are completely missing. Either our understanding of the quantum vacuum is profoundly wrong, or our interpretation of the cosmological constant is flawed, or both. It is a conundrum that lies at the very heart of modern physics, a silent scream from the data that our current models are incomplete and that a deeper, more unified theory of quantum gravity is desperately needed to solve the mystery of dark energy. Faced with this staggering failure of prediction, scientists have been forced to consider a far more radical and dynamic possibility. What if dark energy isn't a fixed property of space at all? What if Einstein's cosmological constant is actually just the simplest answer, and the truth is something much stranger and more fluid? This line of questioning has given rise to one of the most compelling alternative explanations, a concept known as quintessence. The name itself is a nod to antiquity, borrowed from the ancient Greek philosopher's fifth element, the elusive substance that made up the heavenly bodies beyond earth, air, fire, and water. In modern cosmology, quintessence proposes that dark energy is not a constant vacuum energy, but a dynamic field that permeates all of space, a field whose energy density can change over time. This is a fundamental shift in thinking. Instead of a static force baked into the fabric of space-time, quintessence imagines dark energy as something that evolves, much like a weather system moving through the cosmos. This hypothetical field would be a new kind of fundamental force, a cousin to the Higgs field but with repulsive gravitational properties. The key difference from the cosmological constant is that the strength of its repulsive push isn't fixed. In the early universe, this quintessence field could have been weak and dormant, allowing matter to clump together and form galaxies without interference. Then, as the universe expanded and the density of matter diluted, this field could have awakened, its repulsive influence growing until it eventually became the dominant force, kicking the expansion into high gear. This idea of a changing dark energy opens up a breathtaking range of possibilities for the ultimate fate of the cosmos, scenarios far more dramatic than the slow, cold fade offered by a constant cosmological constant. If the strength of dark energy has increased over time, as some quintessence models suggest, it could lead to a truly apocalyptic ending known as the Big Rip. In this scenario, the repulsive force of dark energy doesn't just push galaxies apart. It grows without bound, becoming infinitely strong. First, it would tear apart galaxy clusters, then individual galaxies. As the end draws near, stars would be ripped from their orbits, planets would be shredded from their solar systems, and eventually, the overwhelming force would tear apart every molecule, every atom, and even the very fabric of spacetime itself. The universe would end not with a whimper, but with a violent, fundamental disintegration of reality. Conversely, the field could also decay over time. Perhaps this dark energy is fading, its repulsive power waning. If that were the case, the current acceleration might only be a temporary phase. The cosmos could eventually slow its expansion, with gravity once again taking the reins. This could lead to a future where the expansion halts entirely, potentially even reversing into a big crunch, where the entire universe collapses back in on itself in a fiery finale. The quintessence hypothesis transforms dark energy from a fixed stage into an active, evolving character in the cosmic story, one whose next chapter is still completely unknown. How do we possibly test such an ethereal idea? The answer lies in becoming master cosmic cartographers, creating the most precise three-dimensional map of the universe ever attempted. The goal is to measure the expansion history of the universe with exquisite detail, watching for any subtle changes in the rate of acceleration over billions of years. This is the primary mission of powerful new instruments like the Dark Energy Spectroscopic Instrument, or DESI, mounted on a telescope in Arizona. DESI isn't looking at supernova. Instead, it's meticulously measuring the precise distances to tens of millions of galaxies and quasars. It does this by looking at a specific feature in their light called baryon acoustic oscillations. Billions of years ago, before the first stars formed, the universe was a hot, dense plasma filled with sound waves pulsing through it. These waves created a faint, fossilized imprint, a preferred standard distance that galaxies tend to keep from one another. This distance, about 500 million light-years across, acts as a universal ruler etched into the large-scale structure of the cosmos. By measuring how this ruler appears to stretch at different distances, and therefore different points in cosmic history, DESI can chart the expansion rate with phenomenal precision. Any deviation from the predictions of a simple cosmological constant would be a smoking gun, evidence that dark energy is dynamic, that it is quintessence. The latest data releases are already hinting at fascinating possibilities, suggesting that the density of dark energy might not be perfectly constant, sending waves of excitement through the astrophysics community. The hunt is on to see if these hints solidify into a discovery that would rewrite the textbooks once again. This brings us to one of the most profound questions we can possibly ask: where is all of this headed? The discovery of dark energy didn't just rewrite the history of the cosmos, it completely reshuffled the deck for its ultimate future. We are no longer passive passengers on a ship coasting through space. We are aboard a vessel whose engine is mysteriously and increasingly accelerating, and its final destination is one of three breathtakingly different. For a long time, cosmologists envisioned the end of the universe as a slow, gradual fade, a scenario now known as the Big Freeze or heat death. In this future, the acceleration driven by dark energy continues at a steady, constant rate, just as a cosmological constant would dictate. Billions of years from now, the expansion of space will have carried all other galaxies beyond our cosmic horizon. The night sky, which today is filled with the faint glow of countless distant suns, will go completely and utterly black. Our local group of galaxies, bound together by gravity, may merge into one giant elliptical galaxy, but eventually, even the stars within it will burn through their fuel. One by one, stars will wink out, leaving behind cold stellar remnants, black holes, neutron stars, and white dwarfs. Over trillions upon trillions of years, even these remnants will begin to decay through a process called proton decay, if it exists, or be slowly evaporated by quantum effects near black holes. The universe would approach a state of maximum entropy, a uniform, dark, and frigid void where the temperature approaches absolute zero and no energy is available to power any process forever. It is a quiet, lonely, and profoundly cold ending. But what if dark energy is not constant? If it is a dynamic force like quintessence that grows stronger over time, the finale becomes infinitely more violent and dramatic. This is the realm of the Big Rip. In this scenario, the repulsive force of dark energy doesn't just win out over gravity on the grand scale. It becomes so powerful that it overcomes every single force that holds things together. First, the acceleration would become so extreme that it would tear apart the cosmic web itself, shredding the gravitational bonds that hold galaxy clusters together. Then, individual galaxies would be pulled apart. As the end draws nearer, the overwhelming force would rip stars from their galaxies. Next, it would tear apart our solar system. In the final moments, the force would exceed the gravitational pull holding Earth together, and our planet would be vaporized. The violence wouldn't stop there. The energy would grow so strong it would overcome the electromagnetic force holding molecules together, tearing apart every person, every object, every atom. In the last fraction of a second, it would overcome the strong nuclear force gluing atomic nuclei together, and finally, it would shred the very fabric of spacetime itself. The universe would end in a catastrophic, fundamental disintegration of all reality. There exists a third, more cyclical possibility, the Big Crunch. This scenario requires that dark energy is not a constant and not growing, but is instead fading away. If the repulsive force weakens over time, the acceleration would eventually slow, stop, and then reverse. After its long expansion, the universe would begin to contract. At first, the contraction would be slow, but it would steadily accelerate under the collective pull of all the matter and energy in the cosmos. Galaxies would begin to rush toward each other, their light blue-shifted as space itself shrinks. The temperature of the cosmic microwave background, now a cold whisper, would begin to rise, first to room temperature, then to the temperature of stars. The night sky would glow hotter and brighter. Eventually, all matter and energy would be compressed into an increasingly smaller, hotter, and denser state. The universe would effectively run the film of the Big Bang in reverse, culminating in a fiery collapse back into a singularity, a point of infinite density. Some theories suggest this singularity could then trigger another Big Bang, giving birth to a new universe in an endless cycle of cosmic death and rebirth, a phoenix universe. So which of these fates awaits us? The answer lies in a single, crucial number known as the equation of state parameter, denoted as W. This value describes the relationship between the pressure and density of dark energy. If dark energy is a true cosmological constant, then W equals exactly -1. A value precisely at -1 leads us directly to the Big Freeze. If W is less than -1, meaning the pressure is even more negative, the energy density would increase over time, making the repulsive force stronger as the universe expands. This is the path to the Big Rip. If W is greater than -1, approaching 0, it suggests dark energy could weaken over time, potentially opening the door for a Big Crunch. Current measurements from the most powerful telescopes and instruments, including those from the Planck satellite and the Dark Energy Survey, have pinned down the value of W with increasing precision. The results consistently hover around -1 with a very small margin of error. For now, the data most strongly supports the simplest model, a cosmological constant. This means the current best bet for the ultimate fate of our universe is the long, slow fade of the Big Freeze. However, that margin of error, tiny as it is, still leaves the door open a crack for the more exotic possibilities. The latest data from DAISY, for instance, has hinted that W might not be exactly -1, sending a jolt of excitement through the cosmology community. It's a reminder that the final chapter of our universe's story has not yet been definitively written, and the next generation of telescopes may yet reveal a plot twist more astonishing than any we have yet conceived. Yet this comforting consensus has been shattered by a discrepancy so stubborn and significant that it has escalated into a full-blown crisis in modern cosmology, a puzzle now known as the Hubble tension. The issue is startlingly simple to state and maddeningly difficult to resolve. When we measure the universe's current expansion rate using two different, highly trusted methods, they give us two different answers. It's as if two of the most precise clocks ever built, both built by master craftsmen and ticking with unwavering confidence, persistently tell different times with no clear reason why. This isn't a minor statistical fluke or a small margin of error. The gap between the two values is now so large that the probability it's just a random mistake is less than 1 in a million. This tension suggests that somewhere in our fundamental understanding of the cosmos, a crucial gear may be out of place. One method for telling this cosmic time relies on peering back into the universe's infancy. Scientists use the exquisite details of the cosmic microwave background, the afterglow of the Big Bang, as captured by the Planck satellite. This snapshot from when the universe was only 380,000 years old shows the faint ripples that would eventually grow into galaxies. The standard cosmological model, which includes dark matter and dark energy, allows us to run the universe's film forward from this starting point. By plugging the observed properties of these ripples into the model, cosmologists can predict what the expansion rate should be today. This method provides an answer that is incredibly precise, but it's also indirect. It relies on our complete theoretical understanding of how the universe evolved over billions of years. The other method is far more direct and local. It involves building what astronomers call the cosmic distance ladder. The first rung on this ladder uses straightforward geometry, a technique called parallax, to measure the distances to nearby stars. With these nearby stars as a foundation, astronomers then find stars whose true brightness is known, like Cepheid variables, which pulse at a rate directly tied to their luminosity. By observing how bright these Cepheids appear in relatively nearby galaxies, they can calculate those galaxies' distances. This builds the next rung. Finally, they use those galaxies to calibrate the ultimate standard candles, Type 1, a supernova, the same explosions that revealed dark energy. By comparing the observed brightness of these supernovae in distant galaxies to their known true brightness, they can measure the expansion rate directly. This entire process is like meticulously measuring a mile with a ruler, then using that to calibrate an odometer, and finally driving to see how quickly the landscape is stretching. The profound crisis is that these two impeccable methods no longer agree. The Planck measurement of the early universe predicts a current expansion rate of about 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, a length of about 3.3 million light-years, a galaxy is moving away from us at 67 kilometers per second faster. Meanwhile, the latest results from the Cosmic Distance Ladder, championed by Nobel laureate Adam Rees and his team using the Hubble Space Telescope, consistently find a higher value, around 73 kilometers per second per megaparsec. The universe, according to our local measurements, appears to be expanding about 9% faster than our theory of its beginning says it should be. This might not sound like much, but given the incredible precision of both measurements, this gap is a yawning chasm. It's a discrepancy that refuses to vanish, even as both teams refine their techniques and reduce their error bars. This Hubble tension is not being ignored. It has become the central focus of modern observational cosmology. The scientific response has been to triple-check every single step of both methods, searching for any possible hidden systematic error. Could there be an unknown flaw in how we measure the distances to Cepheid stars? Perhaps interstellar dust is dimming their light in a way we haven't fully accounted for. Maybe the supernova themselves are not perfectly standard candles, and their properties have evolved slightly over cosmic time. Teams around the world have scrutinized every link in the chain. So far, no one has found a convincing experimental error that can explain the gap. In fact, new independent methods are only deepening the mystery. Measurements using the subtle distortions of light from distant galaxies caused by gravitational lensing, and observations of the bright flashes from merging neutron stars are beginning to weigh in, and many are siding with the faster local value. The plot is thickening, not clarifying. The growing consensus is that this tension may not be an error at all, but our first tantalizing glimpse of new physics beyond our current standard model of cosmology. We might be missing a vital ingredient in our cosmic recipe. Perhaps dark energy is not a constant cosmological force but is dynamic, growing stronger over time, which could account for a more recent speed-up in expansion. Or maybe dark matter possesses some previously unknown property, allowing it to interact with itself or with light in a very subtle way that changes how structures form. Another compelling possibility is that the universe contains a new, previously undetected type of relativistic particle, often referred to as dark radiation, which would have flooded the early cosmos and altered how quickly it expanded, throwing off the predictions from the CMB. Each of these ideas is revolutionary, suggesting that the universe is even stranger and more wonderful than we already believe. The Hubble tension is no longer just a problem to be solved. It is a beacon guiding us toward a potentially deeper and more complete understanding of the fundamental forces that have shaped our existence from the very first moment. While the cosmic web is defined by its dense filaments and massive clusters, there is another equally important side to this vast structure: the immense, hauntingly empty spaces in between. These are the cosmic voids, and they are not just simple gaps. They are some of the largest individual structures in the entire universe, vast regions of space that can span hundreds of millions of light years and contain almost nothing. Entering one would be like setting sail on an ocean with no land in sight, where the nearest island is so far away that its light hasn't reached you yet. These voids are not completely empty. A handful of isolated, lonely galaxies might drift through them like solitary ships on a dark sea, but their overall density is thousands of times lower than the bustling galactic metropolises in the clusters and filaments. For a long time, astronomers assumed these voids were simply inert, passive backgrounds, the empty rooms in the cosmic mansion. But more recent observations have revealed something far more strange and active. These voids are not static, they are dynamic and expanding. And they aren't just expanding with the general flow of the universe, they appear to be growing faster than the regions around them. The reason for this accelerated growth is thought to be the overwhelming influence of dark energy. Remember, dark energy is a repulsive force that acts against gravity. In the dense regions of the universe, like galaxy clusters, the powerful gravitational pull of all that matter, both dark and visible, is strong enough to put up a fight, locally resisting the outward push of dark energy. But inside a void, there is very little matter and therefore almost no gravity to counteract it. This allows dark energy to operate unimpeded, essentially pushing on the empty space and causing these voids to expand at an accelerated rate, stretching their boundaries outward faster than the universe's average. This leads to a fascinating and controversial idea that could have a direct impact on one of cosmology's biggest crises. What if our own cosmic address isn't in a typical region of space? What if the Milky Way and our entire local group of galaxies is actually situated inside one of these enormous cosmic voids? This concept is known as the local void hypothesis. If true, it would profoundly affect our perspective on the universe. From our position inside a vast, underdense bubble, our local measurements of the expansion rate would be skewed. The galaxies we use to build the cosmic distance ladder would be receding from us faster than average because the emptiness around us is being pushed apart more vigorously by dark energy. This would mean we are overestimating the global Hubble constant from our local observations. Meanwhile, measurements from the early universe, like the cosmic microwave background, provide a truly global average that isn't affected by this local underdensity. This could potentially explain the Hubble tension, not with new physics, but with a simple yet profound case of our own location bias. Not everyone is convinced by this void solution, however. Creating a void large enough and empty enough to account for the 9% discrepancy in the Hubble constant would require an exceptionally vast underdensity. Some surveys of the large-scale structure around us suggest that while we do reside in a somewhat underdense region, it may not be extreme enough to fully resolve the tension. The debate continues, with astronomers meticulously mapping the galaxies in our cosmic neighborhood to get a better sense of the void's true size and emptiness. Whether it fully solves the mystery or not, the study of voids forces us to confront a humbling possibility that our view of the cosmos and even our measurements of its fundamental properties might be filtered through the lens of our own unremarkable location in an enormous and strangely active nothingness. But if we step back from these separate mysteries, a truly mind-bending question emerges. What if dark matter and dark energy aren't two distinct and unrelated puzzles? What if they are actually connected, two different faces of the very same cosmic phenomenon? This idea might seem counterintuitive at first. One pulls things together with gravity while the other pushes them apart. Yet some of the most brilliant theoretical physicists are now exploring this possibility, suggesting that these two dominant forces of the cosmos could be intertwined in ways we are only beginning to imagine. One of the most provocative ideas in this realm is the concept of an interaction between dark energy and dark matter. In our standard model, these two entities ignore each other completely, operating on the universe in parallel but separate ways. But what if that's not the case? What if they can exchange energy? This isn't as far-fetched as it sounds. We see interactions between fields and particles all the time in the known universe. In these so-called coupled models, dark energy, often represented as a dynamic quintessence field, could slowly decay into dark matter over cosmic time. Alternatively, dark matter particles could annihilate each other, producing dark energy. This kind of conversation between the two could elegantly solve several problems at once. For instance, the observed strength of dark energy is phenomenally weak, a fact that has always been a major puzzle. If it has been slowly converting into dark matter over billions of years, its density would naturally decrease, potentially explaining why it's so faint today. This would also affect the growth of the cosmic web, potentially offering a new explanation for the puzzling scarcity of small satellite galaxies around the Milky Way. Another fascinating proposal flips the script entirely, suggesting that what we perceive as dark matter might actually be an illusion created by dark energy. This idea, sometimes called phantom dark matter, posits that under certain conditions, a particularly strong and dynamic form of dark energy could create effective gravitational fields that mimic the presence of extra mass. Imagine stirring a cup of coffee very quickly. The swirling liquid creates vortices and patterns that have their own structure and behavior. In a similar way, a complex dark energy field evolving over time could create patterns in the fabric of space-time that look and act exactly like the gravitational pull of invisible matter. In this view, we wouldn't need to invent a new particle to explain dark matter because its effects would be a sort of cosmic mirage, a side effect of the true underlying force, dark energy. This would be a truly unified theory, reducing two profound mysteries down to one. Perhaps the most radical approach of all is to question the stage itself. Both dark matter and dark energy are inventions necessitated by the fact that the universe doesn't behave according to Einstein's theory of general relativity on the largest scales. So what if the problem isn't with the contents of the universe, but with the laws of gravity themselves? This brings us back to modified gravity theories like MOND, but on a cosmological scale. The challenge has always been that while MOND works well for individual galaxies, it fails to explain the evidence from galaxy clusters and the cosmic microwave background without adding some dark matter. To overcome this, theorists have been developing more sophisticated versions, often called relativistic modified gravity. These theories aim to tweak Einstein's equations in a consistent way that works across all scales, producing effects that look like both dark matter and dark energy without requiring any exotic substances. These theories propose that our understanding of gravity breaks down not only in the extremely weak field regime of galaxy edges, but also in the low-density, vast expanse of the cosmic web. In these regions, gravity might behave with a subtle difference that perfectly mimics the observed effects of both dark matter's pull and dark energy's push. The holy grail for these models is to simultaneously explain the flat rotation curves of galaxies, the dynamics of the bullet cluster, the pattern of the CMB, and the accelerated expansion, all within a single, modified framework of gravity. It's an immense challenge, but a success here would constitute the most profound revolution in physics since the time of Einstein, fundamentally rewriting our understanding of the most familiar force in the universe. The potential payoff for finding a connection is enormous. A unified theory could provide a single, elegant answer to the universe's composition, revealing a cosmos that is far simpler and more beautiful than our current model of two unrelated, invisible components. It could directly address the Hubble tension. If dark energy and dark matter are interacting, the energy transfer between them would have altered the expansion history of the universe in a way that might perfectly reconcile the early time and late time measurements. It could also solve the "why now?" problem, the curious coincidence that we exist at the precise moment in cosmic history when dark energy has only recently begun to dominate the universe's expansion. If the two are linked, this transition from a matter-dominated to a dark energy-dominated era might be a natural and inevitable phase in their coupled evolution, rather than a bizarre cosmic accident. This search for a connection is more than just theoretical speculation. It is a driving force behind the next generation of astronomical experiments. Projects like the Vera-C, Rubin Observatory, and the European Space Agency's Euclid Space Telescope are designed to map the cosmos with unprecedented precision. They won't just be looking for dark matter or dark energy independently. They will be meticulously measuring the growth of the cosmic web over time and the rate of the universe's expansion to see if their evolution is linked. Any detected correlation, for example, if the amount of clumping in dark matter structures is directly tied to the strength of dark energy's acceleration, would be a monumental smoking gun, the first hard evidence that these two great cosmic mysteries are indeed two sides of the same coin, waiting for a key to unlock their shared secret. But to truly appreciate the power of this cosmic ruler, we have to journey back to a time before the first stars, to a universe that was both incredibly simple and unimaginably violent. For the first several 100,000 years after the Big Bang, the cosmos was a searing hot, opaque plasma, a roiling sea of protons, electrons, and light. Photons of light couldn't travel any meaningful distance before violently scattering off a free electron. It was a thick, blinding fog. Within this plasma, gravity was constantly trying to pull the matter together into denser clumps. But ordinary matter was fighting a powerful opposing force, the immense pressure of the radiation itself. This created a titanic tug of war. Gravity would try to compress the plasma, while radiation pressure would push back, creating powerful spherical sound waves that pulsed outward from every slight over density, rippling through the primordial soup. These weren't gentle waves, they were the most colossal pressure waves the universe has ever known, propagating at a significant fraction of the speed of light. For nearly 400,000 years, this cosmic symphony played out, with waves ringing through the plasma. But then, the universe expanded and cooled just enough for a pivotal moment, one we touched on earlier called recombination. Electrons and protons finally combined to form stable, neutral hydrogen atoms. Suddenly, the fog lifted. The photons, which had been constantly scattering, were set free to travel across the universe in a straight line. This is the light we see today as the cosmic microwave background. But what happened to those mighty sound waves at that exact moment? They froze instantly. The release of the radiation pressure meant the waves stopped propagating. Each wave was caught mid-ripple, imprinting a single, preferred scale onto the distribution of matter, a fossilized echo of the universe's first and only sound. This preferred scale, the distance a sound wave could travel from the Big Bang until that moment of recombination, became a permanent feature of the cosmos. That distance is about 500 million light-years across. After recombination, this imprint acted as a template. Over the next billions of years, as gravity pulled matter together to form the galaxies and clusters we see today, it did so with a distinct preference. Galaxies were much more likely to form at a certain distance from each other, corresponding to the crest of those frozen waves. If you could take a census of all the galaxies in the universe and measure the distances between them, you would find a subtle but statistically overwhelming excess of pairs separated by this specific scale. It's as if the universe has a characteristic groove, a standard spacing that is woven into the very fabric of the cosmic web. This is the Baryon acoustic oscillation, or BAO, and it is this incredibly precise, standard ruler that astronomers now use to measure the geometry and expansion history of the universe with stunning accuracy. The monumental task of finding this faint signal falls to some of the most ambitious sky surveys ever conceived. Projects like the Sloan Digital Sky Survey, or SDSS, and its successor, the Dark Energy Spectroscopic Instrument, or DESI, are essentially creating the largest and most detailed three-dimensional maps of the universe. DESI, mounted on a telescope in Arizona, doesn't take pretty pictures of individual galaxies. Instead, it is a robotic marvel capable of positioning 5,000 individual optical fibers onto 5,000 different galaxies or quasars in a single pointing. Each fiber captures the light from its target, allowing scientists to measure its redshift, the amount its light has been stretched by the expansion of the universe, which tells us its distance. Night after night, DESI is methodically cataloging the precise three-dimensional positions of tens of millions of galaxies, building a map of the cosmic web that stretches across billions of light-years and back in time over 11 billion years. Within this immense, sprawling map of galaxies, scientists then perform a colossal statistical analysis. They look at the clustering of galaxies, measuring how many pairs are found at every possible separation distance. And there, emerging from the noise, is a clear, definitive peak, a specific distance where galaxies are significantly more likely to be found. This is the direct detection of the Baryon acoustic oscillation, the frozen sound wave from the dawn of time. But here's the truly clever part. We know what the true size of this ruler was when it was imprinted. We know it should be exactly 490 million light-years. By measuring how big this ruler appears to be at different distances from us, and therefore at different eras in cosmic history, we can precisely measure how the universe has expanded over time. Think of it like finding a ruler embedded in a photograph of a room, but the ruler is made of a material that expands or contracts with the room itself. If you know the ruler's original length, you can tell if the room has been stretched. DESI and other surveys are doing this not just for one room, but for many different rooms from different eras. They measure the apparent size of the BAO ruler in the nearby universe, the middle distance universe, and the faraway universe. This allows them to construct a detailed history of the expansion rate, watching for any subtle changes that would reveal the influence of dark energy. The latest results from DESI are already providing our most precise measurements yet, and they are painting a fascinating and slightly unsettling picture. The data continues to strongly support the existence of dark energy, but it also contains tantalizing hints that its properties might not be perfectly constant, as Einstein's cosmological constant would suggest. It's as if our cosmic ruler is not just measuring a stretch, but detecting a subtle, accelerating push that may itself be evolving, opening the door to the dynamic quintessence models we discussed earlier. The Baryon acoustic oscillation, a relic from the universe's first second of sound, has become our most trusted instrument for listening to the silent music of dark energy. While the cosmic microwave background and Baryon acoustic oscillations provide a grand view of the universe's expansion history, there exists another, more direct method to measure the cosmos that relies on a celestial quirk of timing. Imagine a distant, brilliant beacon, a quasar, its light streaming across the universe toward us. But on its journey, that light passes near a massive foreground galaxy. According to Einstein's theory, the gravity of that galaxy warps the fabric of spacetime, bending the light and acting like a complex cosmic lens. This gravitational lensing can create a truly spectacular effect. Instead of seeing one quasar, we see multiple copies of it, arranged around the lensing galaxy in a perfect cross or a graceful arc. These aren't different objects, they are multiple images of the exact same event, each one taking a slightly different path around the gravitational well. And because each path has a different length and navigates a different depth of the gravitational field, the light in each image doesn't arrive at Earth at the same time. There can be days, weeks, or even months of delay between when the same flicker of light appears in one image versus another. This isn't a flaw in the observation, it's a feature of the universe itself, and it provides us with an incredibly powerful stopwatch. By carefully measuring these time delays, astronomers can perform a remarkable feat of cosmic reverse engineering. The precise length of the delay depends on two major factors: the total mass distribution of the lensing galaxy, which is predominantly its halo of dark matter, and the overall scale of the universe at the time the light was traveling, which is governed by the expansion rate and the influence of dark energy. This turns these lensed quasars into unique natural laboratories. The time delay gives us a direct measurement of the total gravitational path length, which is shaped by the dark matter. The redshifts of the quasar and the lens give us the cosmic distances involved. By combining these pieces of information, we can effectively weigh the dark matter halo of the lensing galaxy with tremendous precision and simultaneously constrain the expansion rate of the universe. It's a single observation that ties together two of our greatest cosmic mysteries. The longer the time delay, the more mass is present in the lens, telling us about the density and clumpiness of dark matter. And the exact relationship between that delay and the observed distances tells us about the strength of dark energy's push over billions of years. Harnessing this phenomenon requires a level of patience and dedication that borders on the monastic. This is the mission of programs like Cosmological, the Cosmological monitoring of gravitational lenses. For over a decade, this international collaboration has used a network of telescopes around the globe to continuously monitor dozens of these lensed quasars. They take image after image, night after night, year after year, watching for the tiny, predictable flickers in the quasar's brightness to appear first in one image and then, days later, in another. It's a painstaking process, Chinese letter date, to pin down these time delays with an accuracy of better than a few percent. This meticulous work transforms these beautiful cosmic curiosities into some of the most precise instruments we have for measuring the Hubble constant independently, providing a crucial check on the values derived from other methods and adding another vital voice to the conversation surrounding the Hubble tension. Each measured delay is a vote on the true expansion rate of the universe and the nature of the dark matter that guides the light on its journey. To probe the influence of dark energy, cosmologists don't just look at how fast the universe is expanding. They also conduct a massive cosmic census, counting the largest gravitationally bound structures in existence, galaxy clusters. These colossal metropolises, each containing thousands of galaxies, trillions of stars, and vast oceans of hot gas, are the final word in cosmic construction. Their sheer size and mass make them incredibly sensitive barometers for the underlying forces shaping the universe. Think of them as massive weather vanes, the number of clusters that have managed to form by a given time and their distribution across space tells us a profound story about the competition between gravity's relentless pull and dark energy's repulsive push. The logic behind this is beautifully simple. In a universe dominated only by matter, gravity has the final say. It works unimpeded, patiently pulling more and more material into its grasp over billions of years. In such a cosmos, structure formation is an efficient runaway process. Small clumps merge into larger ones, galaxies congregate, and massive clusters should be exceedingly common, forming in great abundance throughout cosmic history. But introduce a significant amount of dark energy and the entire dynamic changes. Dark energy's repulsive effect acts as a sort of cosmic anti-gravity. As the universe expands, the density of matter dilutes, weakening gravity's grip. Meanwhile, if dark energy is a cosmological constant, its energy density remains constant, meaning its repulsive influence becomes ever more dominant over time. This creates a cosmic tug-of-war with a very clear outcome. While gravity is trying to pull matter together to form clusters, dark energy is effectively stretching the very space between the collapsing material, making it harder for gravity to win. It's like trying to climb a hill that is steadily getting steeper as you walk. Dark energy suppresses the growth of structure. It doesn't tear apart existing clusters, but it dramatically slows down the formation of new ones. The consequence is that in a dark energy-dominated universe, we should see a wealth of massive clusters in the distant past, when the expansion was slower and gravity was stronger, but a relative scarcity of new, truly massive clusters forming recently. The cluster population essentially freezes in time. The universe stops making new giants. This is where the counting begins, by taking a detailed census of galaxy clusters across different cosmic epochs, effectively taking snapshots of the universe at ages of 5 billion, 8 billion, and 12 billion years. Scientists can precisely measure this suppression effect. They can trace the growth rate of the cosmic web itself. It requires two crucial measurements for each cluster, its mass and its distance, or redshift. Measuring the mass often relies on the fact that the hot gas trapped in a cluster's gravitational well emits powerful X-rays. The hotter and more luminous the gas, the more massive the cluster must be. The distance is measured by its redshift. By combining these for thousands of clusters, astronomers can build a timeline of structure growth and see exactly when and how dark energy put the brakes on. Pioneering this ambitious endeavor are incredible observatories like the South Pole Telescope, or SPT, located at the most remote and arid place on Earth. Its frigid, stable environment is perfect for observing the faint, cold light of the cosmic microwave background. But the SPT also uses this ancient light as a backlight. As the CMB photons travel across the universe toward us, they pass through the hot electrons in the gas of galaxy clusters. These electrons impart a tiny amount of energy to the photons, leaving a distinct, detectable shadow in the CMB known as the Sunyaev-Zeldovich effect. This allows the SPT to find massive clusters regardless of their distance by the imprint they leave on the universe's oldest light. It has catalogued thousands of clusters this way, many at tremendous distances, providing a deep time view of their abundance. Meanwhile, the EROSIT X-ray telescope, which conducted a full sky survey from space, provides a complementary and incredibly detailed modern census. By scanning the entire sky for the X-ray glow of hot cluster gas, EROSIT has mapped the precise locations and masses of tens of thousands of nearby clusters. This gives us the definitive count of what exists in the universe today. When we compare the prolific cluster formation in the ancient universe, as seen by the SPT, to the more modest number of clusters we see in the contemporary universe from EROSIT, the suppressive fingerprint of dark energy is written plainly across the data. The counts don't lie. The growth of the largest structures in the cosmos has indeed been slowed. and that slowdown aligns perfectly with the presence of a force that is steadily and inexorably accelerating our universe's expansion. If you thought the colossal halos surrounding massive spiral galaxies were mysterious, prepare to shift your gaze to the smallest and most extreme dark matter laboratories in the universe, the dwarf galaxies orbiting our own Milky Way. These tiny, faint collections of stars, often containing only a few thousand or million suns compared to our galaxy's hundreds of billions, are where the rules of dark matter get pushed to their absolute limit. In fact, when it comes to the ratio of dark to visible stuff, these diminutive galaxies aren't just curious outliers, they are the undisputed champions of the cosmos. While a large galaxy like the Milky Way might have roughly 30 times more dark matter than normal matter, some of these orbiting dwarfs have been measured to contain up to 1,000 times more dark matter than everything you can actually see. They are essentially almost pure dark matter with just a sprinkling of stars on top, like a few specks of glitter on an enormous, invisible balloon. To understand why this happens, we need to revisit the cosmic hierarchy of structure formation. The first dark matter halos to collapse after the Big Bang were the small ones. Billions of years ago, these tiny, dense clumps of dark matter served as the gravitational seeds for the very first stars and galaxies. In the largest halos, the process was incredibly efficient. Vast amounts of gas flowed in, cooled, and formed immense numbers of stars, creating the brilliant spiral and elliptical galaxies we see today. But in the smallest halos, the story was very different. Their gravitational pull was much weaker. When the first stars exploded as supernova, their powerful shockwaves could easily overcome the feeble gravity of a small halo, blasting away any remaining gas and shutting down star formation almost entirely. This left behind a failed galaxy, a huge, massive cloud of dark matter that had almost no stars to light it up. The few stars that did manage to form before the gas was ejected are the only visible evidence of the immense, invisible anchor lurking beneath. This is why the darkest galaxies are also the smallest. They are the ones where normal matter was effectively evicted, leaving the dark matter to dominate completely. This bizarre characteristic makes dwarf galaxies a phenomenal natural experiment, because they are so utterly dominated by gravity, with very few complicating factors like magnetic fields or intense stellar feedback. Their internal structure should, in theory, provide an incredibly clean map of their dark matter halos. By carefully tracking the motions of their stars, astronomers can chart the gravitational field and reconstruct the density and distribution of the unseen mass with high precision. What they've found is that many of these galaxies have dark matter that is intensely concentrated at their centers, forming what is known as a cusp, a sharp peak in density. This was exactly what the most popular cold dark matter simulations had predicted for decades, and for a while it seemed like a resounding victory for the theory. However, as observations improved, a problem emerged. Other dwarf galaxies seem to show a much shallower distribution, with a constant density core of dark matter at their center instead of a steep cusp. This apparent contradiction sparked a major debate. Was this evidence that dark matter might have some unknown property allowing it to interact with itself, effectively smoothing out the central cusp? Or were astronomers simply underestimating the complex role of ordinary matter? We now know that even a small number of stars can have an outsized impact. When massive stars go supernova, the explosions can pump energy into the central regions, causing gas to slosh in and out. This rhythmic motion can actually gravitationally drag the dark matter with it, slowly pulling it outward and eroding the central cusp into a core over billions of years. So the observed cores might not contradict the cold dark matter model at all, but instead reveal a fascinating and previously overlooked cosmic dance between the dark universe and the visible one. But the puzzles don't end there. An even more perplexing problem emerged from the other side of the simulation ledger, known as the too big to fail problem. Our most sophisticated supercomputer models of dark matter halos don't just predict the existence of the small, star-poor halos we see. They predict that the Milky Way should be surrounded by hundreds of them. More importantly, they predict that many of these halos should be quite massive, are too big to have failed at forming a significant number of stars. According to the simulations, we should be able to look out and see dozens of large, bright dwarf galaxies orbiting us. But when we conduct a census, we only find a handful. The most massive dark matter halos predicted by the models appear to be entirely missing their visible galaxies. It's as if we've taken a cosmic head count and discovered that all the biggest, most imposing neighborhoods in our galactic city are completely empty and dark. This startling discrepancy forced theorists to go back to the drawing board. One compelling solution suggests that our models of star formation in the earliest, smallest galaxies were far too simplistic. The ultraviolet radiation from the very first stars could have been so intense that it heated the cosmic gas everywhere, making it incredibly difficult for that gas to cool down and collapse into the smaller halos, effectively starving them of the fuel needed to form stars. Another, more radical possibility is that this is our first tangible clue about the fundamental nature of the dark matter particle itself. The standard cold model assumes these particles move slowly and interact only through gravity. But if a fraction of dark matter were slightly warm, meaning the particles moved with more speed and energy in the early universe, it would have a profound effect. These faster-moving particles would have found it much more difficult to clump together on the smallest scales. This would naturally wipe out the smallest subhalos and reduce the central density of the remaining ones, potentially explaining why we don't see as many large dwarf galaxies as the pure cold dark matter model predicts. The dwarf galaxies we can see, therefore, are not just cosmic curiosities. They are the critical forensic evidence in an ongoing investigation, their very existence and structure placing some of the tightest constraints we have on what dark matter actually is. While the search for dark matter has largely been defined by what we haven't found, one experiment has spent over 2 decades reporting a persistent, tantalizing signal that refuses to go away. It's a claim that has become one of the most enduring and contentious mysteries in all of modern physics. Nestled deep within the Gran Sasso mountain in Italy, shielded from cosmic rays by 1,400 meters of rock, the Dama/Libra experiment has been quietly collecting data since the late 1990s. Unlike other detectors that use noble liquids like xenon, Dama employs a different strategy. Its core is made of extremely pure sodium iodide crystals. The premise is that if a dark matter particle, specifically a WIMP, were to collide with a nucleus in one of these crystals, it would produce a tiny flash of light, a scintillation that sensitive photomultiplier tubes can detect. The extraordinary claim from the Dama team is not that they've seen a handful of these events, but that they have observed a very specific repeating pattern in their data, a signal that modulates or rises and falls with a period of exactly 1 year. This is the annual modulation signal, and its potential implications are staggering. The reasoning behind it is beautifully elegant. Our solar system is orbiting the center of the Milky Way galaxy, and as it does so, it is moving through the vast, stationary halo of dark matter that envelops us. But we on Earth have a second motion. We are also traveling around the Sun at a speed of about 30 kilometers per second. This means that around June, Earth's motion around the Sun is adding to the solar system's motion through the galaxy. We are effectively moving into the dark matter wind, like a car driving into a gentle rain, which should increase the relative velocity and thus the number of collisions with dark matter particles in our detectors. 6 months later, in December, Earth's orbital motion is in the opposite direction. So we are moving with the dark matter wind, reducing the relative velocity and the expected collision rate. The Dama collaboration asserts they have seen this exact sine wave pattern repeating with high statistical significance for over 20 years, a rhythmic ticking that they argue is the first direct detection of dark matter. The scientific community's reaction to this claim has been a mixture of intense skepticism and fascinated intrigue. The primary reason for doubt is that no other experiment, using a variety of different target materials and technologies, has been able to reproduce this result. Experiments far larger and more sensitive than DARMA, like Xenon 1T and LUX, have seen no sign of an annual modulation that matches DARMA's signal. Critics point to a host of potential systematic effects that could mimic such a pattern. Seasonal variations in the underground laboratory itself are a major concern. Changes in temperature, humidity, or even the water table above the lab between summer and winter could subtly affect the electronics and create a false annual signal. There's also the possibility of backgrounds from cosmic rays that somehow vary annually, or from neutrons produced by natural radioactivity in the surrounding rock whose flux might change with the seasons. To definitively test the DARMA result, several new experiments have been built or are in development, all using the same sodium iodide crystal target to eliminate any doubt about the material itself. The goal is to see if the signal replicates under the same conditions, but with improved controls to rule out those pesky seasonal systematics. Experiments like Cosine 100 in South Korea and ANICE in Spain have been taking data for years. Their initial results have not confirmed the DARMA signal, but they also haven't yet collected enough data to completely rule it out with the same statistical certainty. The plot thickened further when the SABRE experiment, which plans to operate identical detectors in both the northern and southern hemispheres, pointed out a clever test. If the signal is truly from a dark matter wind, the modulation should be exactly 6 months out of phase between the two hemispheres. When it's summer in Italy, it's winter in Australia. A seasonal environmental effect, on the other hand, would follow the local seasons and not be phase-flipped. The enduring mystery of DARMA is a perfect microcosm of the scientific process at its most challenging. It pits a long-standing, statistically robust observation against a complete lack of confirmation from any other source. It forces us to ask difficult questions. Is DARMA seeing something incredibly exotic that other experiments are blind to, perhaps because of the unique properties of their sodium iodide crystals? Or have they been tragically misled for decades by a subtle, unaccounted for environmental effect? Resolving this puzzle is crucial, not just for the teams involved, but for the entire field. A confirmation would be the crowning achievement of decades of research, finally opening a window into the dark universe. A final, definitive refutation, however, would be equally important, allowing physicists to close a long and distracting chapter and focus their efforts entirely on new and more promising avenues in the great hunt for the universe's missing mass. While our largest telescopes map the cosmos and our most sensitive detectors listen for ghostly particles, some of the most profound clues might come from tuning into the universe's oldest radio station, broadcast on a very specific and quiet frequency. This brings us to a claim so unexpected that it has sent shockwaves through the world of cosmology, a potential discovery that could rewrite the first chapters of our cosmic history and reveal an entirely new facet of dark matter's nature. It's a mystery that begins not with a bang, but with a deep and puzzling absorption signal in the faintest radio waves from the dawn of time. To understand this, we have to go back to that pivotal moment a few 100,000 years after the Big Bang, when the universe cooled enough to form the first atoms. As that hot, opaque plasma of particles cleared, it left behind a vast, dark sea of neutral hydrogen gas. This gas would fill the cosmos for the next several 100 million years, a featureless void before the first stars. But this hydrogen was not completely silent. Each atom is like a tiny magnet with the spin of its single electron and proton capable of being aligned or opposite. Flipping from the higher energy, aligned state to the lower energy, opposite state causes the atom to emit a photon with a very specific wavelength, 21 centimeters. This is a radio wave, and it provides a direct window into the conditions of the early universe. The EDGES experiment, a deceptively simple array of radio antennas in the remote deserts of Western Australia, was built for one purpose: to detect the faint echo of this 21-centimeter signal from the cosmic dawn. The theory was straightforward. When the very first stars and galaxies began to ignite, their intense ultraviolet light would have excited the surrounding hydrogen gas, pumping the atoms into their higher energy state. This should have created a detectable absorption dip in the background radio spectrum, a signature of the gas being excited and then emitting these 21-centimeter photons. In 2018, the EDGES team announced they had found it, but the signal they detected was not just a quiet dip. It was an enormous trough, twice as deep as any cosmological model had ever predicted. It was as if they were listening for a gentle whisper and instead heard a cavernous echo. This anomalous depth suggests something truly bizarre was happening to that primordial hydrogen gas. The strength of an absorption signal is directly tied to the temperature difference between the hydrogen gas and the background radiation it's silhouetted against. For the signal to be so strong, the hydrogen must have been significantly colder than anyone thought possible. The cosmic microwave background radiation at that time had cooled to a temperature of a few tens of degrees Kelvin. Standard physics suggests the hydrogen gas should have been even warmer than that due to interactions with the surrounding matter. But the EDGES data implies the gas was shockingly cold, almost half the expected temperature. Something or someone had to be running a cosmic air conditioner on the early universe, siphoning away heat from the hydrogen at an incredible rate. This is where the plot thickens and dark matter enters the scene as a prime suspect. Could this be the first direct evidence of an interaction between dark matter and normal matter beyond gravity? The leading hypothesis is that a certain type of dark matter particle, potentially very light and able to bounce off normal matter, could have acted as a heat sink. If these dark matter particles were cooler than the hydrogen gas and possessed a slight ability to interact with it, every collision would have drained thermal energy from the gas, chilling it dramatically. It's a radical idea, suggesting that dark matter isn't completely inert and aloof. In the universe's infancy, it may have reached out and touched the visible world, leaving a fingerprint in the radio static. Unsurprisingly, a claim this extraordinary has been met with intense scrutiny and vigorous debate. The primary challenge is that the signal EDGES is trying to detect is incredibly faint, buried under a sea of radio interference from our own galaxy and Earth-based sources that are thousands of times stronger. Extracting it requires painstaking calibration and sophisticated modeling to subtract this overwhelming foreground noise. Many critics argue that the observed deep trough is not a signal from the cosmic dawn at all, but an artifact of an imperfect foreground subtraction. They suggest that a tiny, unaccounted-for ripple in the model of our own galaxy's radio emissions could easily mimic the precise shape of the absorption feature the EDGES team reported. It's like trying to hear a single soft note in a roaring symphony hall. If your understanding of the orchestra's sound is off by even a fraction, you might imagine a note that was never played. The scientific process is now working as it should, with multiple teams building next-generation experiments to either confirm or refute the astounding EDGES result. Projects like PRISM, CERES, and the upcoming Lunar Surface Electromagnetics experiment aim to measure the same signal with different instruments, methodologies, and in even more radio-quiet environments, including the far side of the Moon. If these independent experiments also detect this anomalously deep absorption line, it will be a monumental breakthrough, forcing a fundamental rewrite of the particle physics rulebook and finally giving us a specific property to pin on dark matter. If they find nothing, it will stand as a powerful lesson in the immense challenges of precision cosmology. Either way, the quest to explain that mysterious dip is pushing our technological limits and deepening our understanding of the universe's first and most fragile light. Yet just when we thought we had a handle on this invisible cosmic architecture, a new layer of mystery emerged, one that has sent both dark matter and modified gravity theorists back to their chalkboards. For decades, the evidence seemed beautifully consistent. All spiral galaxies had flat rotation curves, all of them required dark matter halos. But as our telescopes peered deeper and our surveys grew more comprehensive, we began to see that the universe is far less uniform than we assumed. We've now entered an era of precision galaxy rotation measurements, and the data reveals a startling and unexpected diversity that challenges the very core of both competing theories. This mystery centers on a growing catalog of galaxies whose behavior defies easy categorization. On one end of the spectrum, we have galaxies like Dragonfly 44, a diffuse object in the Coma cluster that is so incredibly dim it was almost missed entirely. But when astronomers measured the velocities of its stars, they were stunned. The stars were moving so fast that the galaxy must be composed of 99.99% dark matter. It is a ghostly sail of stars adrift in an unimaginably vast sea of invisible matter, a halo so massive it rivals that of our own Milky Way, yet with almost none of the stellar brilliance. This galaxy is almost pure dark matter. Then, at the opposite extreme, we have the confounding case of galaxies like NGC 1052 DF2 and its sibling DF4. These are also ultra-diffuse galaxies, but they present a mirror image puzzle. Measurements of the motions of their star clusters and planetary nebulae show something that was once thought to be impossible. They are moving with startling slowness. The calculated mass from these motions aligns almost perfectly with the mass of the stars and gas we can see. These galaxies appear to have little to no dark matter at all. For the dark matter model, this is deeply puzzling. How could a galaxy form within a dark matter halo and then somehow become completely divorced from it? For modified gravity theories like MOND, the problem is even more acute. If the observed acceleration is so low that it falls below MOND critical threshold, the theory predicts a very specific boost to gravity that should make the stars move faster. But in these galaxies, that boost is conspicuously absent. They rotate exactly as Newton's unmodified laws would predict, a result that is just as damaging to MOND as it is to the standard model. This incredible diversity from dark matter dominated to dark matter deficient creates a paradox that simple versions of both theories struggle to explain. It suggests that the relationship between dark matter and the visible galaxy is not a simple one-to-one correlation. Something much more complex and nuanced is at play in the galaxy formation process. One compelling explanation is that we are witnessing the dramatic aftermath of ancient cosmic collisions. Galaxies are not isolated islands. They exist in a dynamic and often violent environment. A dark matter deficient galaxy like DF2 might have been the victim of a high-speed encounter with a much larger galaxy. In this scenario, the collision could have been a kind of cosmic gutting. The more resilient stars and star clusters which interact through gravity could have been stripped away from their original dark matter halo, which itself interacts only through gravity and would have been unaffected by the hydrodynamic drag that affects gas. The visible galaxy and its dark matter cloak become separated, creating a trail of dark matter-free stellar systems. This would explain the deficiency, but it requires a very specific and relatively rare set of collision parameters, making the existence of several such galaxies a puzzle in itself. Alternatively, the answer may lie in the feedback from star formation itself. The first generations of stars in a small galaxy were titanic and short-lived, exploding as supernova in a relentless series of blasts. In a low-mass dark matter halo with a weak gravitational grip, these powerful explosions could have been energetic enough to literally blow all of the remaining gas and dust right out of the galaxy. Without this gas, no new stars could form, and the existing stars would be left orbiting in a halo that was itself being eroded by tidal forces from nearby galaxies over billions of years. The final result could be a galaxy that has effectively evaporated away most of its dark matter, leaving behind a faint dark matter poor relic. The existence of this spectrum from the dark to the bright forces a profound shift in our perspective. It tells us that galaxy formation is not a monolithic process but a rich tapestry of events where dark matter provides the foundational gravity, but the visible matter has a story of its own. The complex interplay of mergers, collisions, and the furious energy output of stars themselves can sculpt, rearrange, and even sever the connection between what we see and the unseen mass that holds it all together. This diversity isn't a contradiction of the dark matter hypothesis. Rather, it is a challenge to our understanding of galaxy evolution within that framework. It demands more sophisticated models that can account for this full range of outcomes, showing us that the universe is not just stranger than we imagined, but also more inventive in the ways it assembles and disassembles the structures within it. But to truly grasp how dark energy is reshaping our local cosmic environment, we need to understand a fundamental concept known as the Hubble flow. Imagine the universe not as a collection of static objects, but as an immense, rising loaf of raisin bread baking in an oven. Each raisin is a galaxy. As the dough expands, every raisin moves away from every other raisin. The farther apart any two raisins are, the more dough there is between them to expand, and the faster they appear to be moving apart. This smooth, overall expansion of the cosmos is the Hubble flow. For most of the 20th century, we assumed this flow was uniform and steady, a simple and predictable backdrop against which the gravitational dances of galaxies played out. However, dark energy has introduced a shocking twist to this story. Its repulsive force doesn't just cause a steady expansion, it causes an accelerating expansion. This means the Hubble flow isn't a constant river, it's a river that's flowing faster and faster over time, and this acceleration isn't happening equally everywhere at once. Its influence depends on the local strength of gravity. Within the gravitational grasp of a massive structure like the Virgo cluster, which our local group of galaxies is slowly falling towards, gravity is still the dominant force. Galaxies here are bound together, resisting the overall expansion. But as we look beyond these local gravitational wells into the vast, emptier regions of space, the countervailing pull of matter weakens dramatically. Here, with nothing to oppose it, dark energy's push becomes the overwhelming force, and the pure, accelerating Hubble flow takes over. This creates a fascinating and measurable transition zone in the space around us. Astronomers can now map this cosmic frontier with incredible precision by measuring the distances and velocities of thousands of nearby galaxies. They use the same cosmic distance ladder techniques involving Cepheid variables and Type 1, a supernova, but they focus on objects within a few 100 million light-years. By doing this, they aren't just measuring a single number for the Hubble constant. They are creating a detailed topographical map of the local expansion rate. They can see the exact point where the peculiar motions induced by the gravitational tug of the Great Attractor and other local superclusters finally give way to the smooth, dark energy-driven flow of the wider universe. It's like measuring the currents in a river and identifying the precise point where the chaotic swirls near the bank finally smooth out into the fast-moving water of the main channel. The latest results from these local surveys have revealed something that is both surprising and deeply puzzling. When astronomers calculate the expansion rate using these very nearby galaxies, they often get a value that is slightly higher than the rate measured from the global, universe-wide average. This suggests that our local region of space, out to a few 100 million light-years, might be expanding a bit faster than the rest of the cosmos. At first glance, this seems to contradict the very idea of a uniform Hubble flow. How can the expansion rate be different here than it is over there? The most intriguing explanation points to a radical possibility that dark energy itself might not be perfectly smooth. What if the distribution of this mysterious energy isn't completely uniform across the cosmos? The standard model of cosmology assumes it is a feature of space itself that is the same everywhere. But what if that's not entirely true? This idea of inhomogeneous dark energy suggests that the density of this repulsive force could have slight variations, much like matter has variations that form galaxies and voids. We might be residing inside a region where the dark energy density is slightly lower than the cosmic average. If that were the case, the expansion history of our local volume would be slightly different. With less repulsive push holding it back, the gravitational collapse of matter in our past would have been more efficient, making our local universe a bit more underdense than other regions. An underdense region, as we've learned from studying cosmic voids, expands faster because there's less gravitational mass to slow it down. Therefore, our local measurement of the Hubble constant would be E Chinese letter, not because of a fundamental error, but because we are living in a slightly atypical bubble where the rules of expansion are subtly different. This wouldn't just be a curiosity, it would be a direct challenge to the cosmological principle, the foundational idea that the universe is homogeneous and isotropic on large scales. It would mean that not only is the distribution of matter lumpy, but the very force shaping the fate of the cosmos might be as well, adding yet another layer of profound mystery to the dark energy enigma. While the vast cosmic web and massive galaxy clusters represent the grandest scales of dark matter's influence, some of its most profound secrets may be hidden in structures so tiny they defy imagination. If we could rewind the cosmic film all the way back to the universe's first moments, we would witness an astonishing process unfolding in the absolute darkness. Long before the first stars flickered to life, even before the cosmic microwave background was emitted, the very first structures were already beginning to form. These were not majestic galaxies or brilliant quasars, but inconceivably small and dense knots of pure dark matter known as microhalos. The formation of these miniature structures is a direct prediction of our most successful cosmological models, and finding evidence for them could unlock a new chapter in our understanding of the invisible universe. The story of microhalos begins with the initial conditions of the cosmos. The early universe was not perfectly smooth. It was imprinted with tiny quantum fluctuations that were stretched to cosmic scales during a period of rapid inflation. These microscopic ripples in the fabric of space-time represented the seeds of all future structure. For normal matter, forming clumps was a struggle against the intense radiation pressure that filled space. But dark matter, unaffected by light, was free to immediately respond to gravity's relentless pull. The smallest of these initial overdensities, regions where dark matter was ever so slightly more concentrated, began collapsing under their own gravity when the universe was less than a year old. The result was the formation of Earth mass clumps of dark matter, packing the gravitational punch of our entire planet into a region of space no larger than our solar system. These microhalos are the primordial building blocks of the cosmic web, the very first structures of any kind to emerge from the Big Bang's aftermath. Their existence is more than just a theoretical curiosity. It is a critical test for the cold dark matter paradigm. The standard model assumes dark matter particles move relatively slowly, allowing them to efficiently clump together on these incredibly small scales. If dark matter were warm, meaning the particles had too much thermal motion in the early universe, they would have washed out these tiny fluctuations, preventing microhalos from forming. Therefore, the presence or absence of these structures acts as a powerful diagnostic tool. Discovering microhalos would provide rock-solid confirmation that dark matter is indeed cold, while failing to find them would force a major rethink, potentially pointing toward warmer, more exotic particle candidates. They are a direct window into the fundamental properties of the dark matter particle itself. But how do you search for something that is not only invisible but also smaller than a star and made of a substance that barely interacts with anything? Astronomers have devised two brilliantly indirect methods to hunt for these cosmic ghosts. The first approach looks for the faint, telltale glow of their annihilation. If dark matter is made of particles that are their own antiparticles, such as WIMP, then whenever two of them collide, they could annihilate in a flash of energy, producing gamma-ray photons. A dense Earth mass microhalo would be a perfect factory for such events. While a single microhalo would be too faint to see individually, a large population of them lurking in the halo of our Milky Way could create a subtle, additional component of diffuse gamma-ray light superimposed on other astrophysical sources. By meticulously analyzing the energy spectrum and distribution of gamma rays collected by telescopes like the Fermi Gamma Ray Space Telescope, scientists hope to find an anomalous signal that can't be explained by pulsars or supernova remnants, a faint whisper from the universe's very first structures. The second technique is even more ingenious, using the universe itself as a magnifying glass through a phenomenon called gravitational microlensing. According to Einstein's theory of general relativity, a massive object will bend and focus light from a background star. If a compact, dense object like a microhalo were to pass directly between us and a distant star, it would act as a temporary lens, causing the star to briefly brighten in a very specific and predictable way. Massive surveys that monitor hundreds of millions of stars, like the optical gravitational lensing experiment or the upcoming Vera-C Rubin Observatory, are on the constant lookout for these fleeting flashes. While most microlensing events are caused by faint stars, brown dwarfs, or rogue planets, a subset of events could be the signature of Earth mass objects that emit no light whatsoever, a compelling, if indirect, detection of a dark matter microhalo in motion. The quest to find these primordial relics is about more than just ticking a box in a theoretical model. It represents a journey to the very beginning of structure formation, allowing us to test our understanding of the universe in a regime that is otherwise completely inaccessible. Confirming the existence of microhalos would do more than verify that dark matter is cold. It would open up an entirely new field of study, dark matter archaeology. By studying their predicted numbers and distribution, we could learn about the spectrum of those initial inflationary ripples, the smallest scales on which they operated. We could understand how these first microhalos later merged and assembled into the larger subhalos and galaxies we see today, tracing the full growth history of the cosmic web from its tiniest seeds to its largest nodes. These tiny, ancient clumps are the missing link between the smooth, early universe and the richly structured cosmos we inhabit, holding within their invisible grasp the story of how darkness first gave form to the universe. What if the key to unlocking the dark matter puzzle isn't a new particle, but something we already know exists, just in a radically different form? This brings us to one of the most compelling and controversial ideas in modern cosmology, the possibility that dark matter is made of black holes. But not the kind of black holes formed from dying stars. We're talking about primordial black holes, hypothetical objects forged in the unimaginable chaos of the universe's very first second. The concept is as elegant as it is audacious. Moments after the Big Bang, when the cosmos was a seething, ultra-dense soup of energy, random quantum fluctuations could have created pockets of space so intensely dense that they collapsed directly into black holes. These wouldn't be the result of stellar collapse. They would be a fundamental product of creation itself, born from the raw energy of the infant universe. If these objects formed in vast numbers, they could be everywhere, invisible, barely interacting, yet exerting a powerful gravitational pull, a perfect description of the dark matter that has eluded us for decades. For a long time, this idea was largely sidelined, considered an interesting but unlikely alternative to the more popular WIMP and axion models. That all changed dramatically in 2015 with a single earth-shaking discovery. The LIGO Observatory detected the first ever gravitational waves, ripples in space-time caused by the collision of two black holes over 1 billion light-years away. The discovery was monumental on its own, but the properties of these black holes sent a jolt through the astrophysics community. They were heavy, each about 30 times the mass of our Sun. In our current understanding of stellar evolution, black holes that form from dying stars are typically either much smaller, around 5 to 10 solar masses, or much larger, the supermassive beasts at the centers of galaxies. A black hole of 30 solar masses is in a puzzling middle ground, a bit too hefty to easily form from a single star's death. This immediately led to a thrilling question: what if the black holes LIGO saw weren't stellar remnants at all? What if they were primordial, dating back to the beginning of time? And if such objects were common enough to merge and be detected by LIGO, could they possibly make up the dark matter? This revelation catapulted the primordial black hole hypothesis from a fringe thought to a serious area of investigation. The appeal is undeniable. It would solve two profound mysteries with one elegant solution: identifying the dark matter and explaining LIGO's surprising observations simultaneously. We wouldn't need to invent a new, never-before-seen particle. We could simply be surrounded by a vast, unseen population of ancient black holes, their collective gravity weaving the cosmic web. Their darkness and inability to interact with light would perfectly match the observed behavior of dark matter. It's a beautifully simple and powerful idea. However, a compelling hypothesis must survive confrontation with data, and the universe has provided us with several powerful ways to test it. The most significant constraints come from a technique we've discussed before: microlensing. The principle is straightforward. If a massive, compact object like a black hole passes directly between us and a distant star, its gravity will act as a lens, bending the starlight and causing the star to temporarily brighten. If the halo of our Milky Way were teeming with primordial black holes, they should be constantly drifting in front of the countless stars in nearby galaxies like the Large and Small Magellanic Clouds. Major surveys, most notably the Macho and Eros projects, spent years monitoring millions of stars, patiently waiting for these telltale flashes. Their results were definitive. They did see a handful of microlensing events, likely caused by known, ordinary objects like faint stars or white dwarfs. But they did not see the thousands of events that would be expected if a significant portion of the dark matter were made of black holes in the specific mass range of 1 to 100 solar masses. These surveys effectively ruled out the possibility that such black holes could be the primary component of dark matter, but the investigation didn't stop there. Astronomers have used other clever observations to close other mass windows. For instance, the way primordial black holes would gravitationally lens the light from distant supernova could distort their apparent brightness in a way we don't observe. The incredible precision of the cosmic microwave background also places strict limits. If too many primordial black holes existed, their accretion of matter in the early universe would have injected extra energy into the primordial gas, leaving a detectable imprint on the CMB's delicate temperature patterns, an imprint that so far is absent. Even the tight orbits of stars within dwarf galaxies and the pristine structures of the oldest star clusters in the Milky Way would be disrupted if they were swarming with black holes, acting like gravitational ping-pong balls knocking the stars around. Each of these independent lines of evidence paints the same picture. While some primordial black holes could certainly exist, they cannot account for all or even most of the dark matter. So where does this leave the idea? It forces a fascinating refinement. The constraints aren't absolute across all possible masses. There are still narrow, open windows where primordial black holes could exist in large numbers without contradicting the data. Perhaps they are all very, very light, with masses less than that of an asteroid. These would be too small to create a detectable microlensing signal, yet could collectively have enough mass. Or conversely, perhaps they are incredibly heavy, each 1,000th of times the mass of the Sun. These would be so rare that microlensing surveys wouldn't have seen enough of them, yet a few could anchor the dark matter halos of dwarf galaxies. The LIGO observations keep the hope alive for this middle weight range, suggesting that while they can't be 100% of the dark matter, they might still be a small but interesting component of it. The search continues not for a singular answer, but for a potential population of these ancient relics hiding in the gaps of our observations, a reminder that the dark universe may be composed of more than one type of hidden ingredient. Imagine a force so shy that it only shows its true strength in the most profound emptiness, a cosmic push that hides itself away in crowded galactic cities. This is the startling possibility at the heart of the symmetron hypothesis, a theory proposing that dark energy isn't a constant, unchanging force but a dynamic field whose influence depends entirely on its surroundings. The name symmetron comes from the idea of symmetry, a fundamental concept in physics that often signifies a stable, balanced state. The theory suggests that this field exists in a perfectly symmetrical, high-energy state in the vacuum of empty space. But in the presence of matter, this symmetry is broken and the field effectively shuts down, its energy and influence dropping to nearly zero. It's a chameleon force, changing its behavior based on the local density of the universe. To grasp this, picture a peculiar kind of cosmic spotlight that only shines brightly on a completely dark stage. In the vast, near-perfect emptiness of a cosmic void, where the density of matter is almost zero, the symmetron field would be free to operate at its full potential. Here, it would exert its maximum repulsive force, pushing space apart and contributing to the accelerated expansion we attribute to dark energy. But now, imagine that spotlight turning toward a populated area, a galaxy cluster teeming with stars, gas, and dark matter. The presence of all this mass would act like someone flipping a switch, causing the symmetron field to instantly dim. Its repulsive power would vanish in these dense environments. This elegantly explains why we don't feel this incredible anti-gravity force here on Earth or within our solar system. We are living in a relatively dense neighborhood, so the symmetron field is in its off state, its effects completely masked by the matter all around us. This idea of an environmentally dependent force is part of a broader class of theories involving so-called fifth forces. We are familiar with the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. If a symmetron field exists, it would represent a fifth fundamental force, one that has remained hidden because of its elusive, density-dependent nature. This isn't just wild speculation. It's a serious attempt to solve some of the most annoying fine-tuning problems in cosmology, such as the infamous cosmological constant problem. Why is the observed strength of dark energy so unimaginably weaker than what quantum theory predicts? The symmetron model offers an answer. The value we measure is not the field's true, intrinsic strength, but merely its effective strength in the low-density environment of the cosmic voids. Its true potential is only revealed in the deepest emptiness. The hunt for this hidden force is underway on two fronts, in the cosmos and in the laboratory. Astronomers are meticulously comparing the structure of the universe in dense regions versus empty voids. If the symmetron idea is correct, the accelerated expansion should be slightly more pronounced in the most perfect voids, and the growth of galaxy clusters might be subtly different at the boundaries where high-density regions meet the empty expanse. By mapping the universe in 3 dimensions with instruments like the Dark Energy Spectroscopic Instrument, scientists are looking for these telltale environmental signatures. Meanwhile, physicists are designing incredibly sensitive tabletop experiments to try and detect the symmetron field directly here on Earth. These experiments don't look for the large-scale repulsive effect, which is switched off locally. Instead, they search for extremely faint, short-range forces between objects. The technique often involves measuring the infinitesimal attraction between 2 precisely crafted masses in a high vacuum chamber. looking for any deviation from the predictable pull of gravity that could be the signature of a fifth force mediated by the symmetron. While no definitive signal has been found yet, the search itself is pushing the boundaries of precision measurement, proving that even the universe's grandest mysteries might be unraveled by the most delicate of experiments. While the grand halo of our Milky Way seems like a vast and placid sea of dark matter from a distance, a closer look reveals a far more dynamic and even violent history. Our galaxy did not form in peaceful isolation. It grew over billions of years by consuming smaller neighbors in a process of relentless cosmic cannibalism. As a dwarf galaxy is drawn into the Milky Way's immense gravitational grasp, it doesn't just vanish. It is slowly, methodically torn apart. The relentless tidal forces, the difference in gravity between the side of the galaxy closest to us and the side farthest away, act like a cosmic chef pulling apart a piece of pulled pork, stretching the victim galaxy into a long, thin river of stars, gas, and of course, dark matter. These are galactic stellar streams, and they are the ghostly fossils of ancient mergers, weaving through the halo like celestial ribbons. For a long time, these structures were incredibly difficult to see. Their stars are sparse and spread over enormous distances, making them nearly invisible against the crowded backdrop of the Milky Way's own stellar population. That all changed with a revolutionary European Space Agency mission named Gaia. Launched in 2013, Gaia is not just a telescope, it is the most ambitious astrometric survey ever conceived. Its goal is to create an unprecedented three-dimensional map of our galaxy by precisely measuring the positions, distances, and motions of over 1 billion stars. It's like giving the Milky Way a full-body MRI scan. By tracking how stars move, Gaia allows us to not only see the present structure of our galaxy, but to rewind the cosmic film and see where they have been. This has unveiled a hidden universe of structure within the halo, revealing that our galaxy is crisscrossed with dozens of these stellar streams, each one the lingering signature of a separate galactic meal consumed long ago. The discovery that truly sent shockwaves through the astrophysics community is known as the S1 stream. Unlike most streams that orbit safely in the distant halo, data from Gaia revealed that S1 is something entirely different. It is a massive current of stars and accompanying dark matter that is on a radical, plunging orbit, one that carries it directly through our own cosmic neighborhood, the region of space occupied by our solar system. This means that right now, as you watch this, our sun is passing through a filament of stars and invisible matter that was once part of a distinct galaxy that our Milky Way devoured in the distant past. We are quite literally sailing through the ghost of a galaxy that died long before our own sun was even born. This has profound implications for the century-long hunt to detect dark matter particles. Most experiments are designed to look for a smooth, uniform wind of dark matter particles blowing through Earth as we orbit the galactic center. But the presence of the S1 stream suggests that the local dark matter distribution might not be smooth at all. It could be lumpy, filled with dense clumps and currents. If our solar system is currently immersed in this stream, the local density of dark matter could be significantly enhanced, creating a temporary but powerful surge in the number of particles passing through our detectors every second. It's the difference between trying to catch a few stray drops of rain and suddenly finding yourself in the heart of a downpour. This gives scientists a specific and predictable time frame to look for a stronger signal, a potential breakthrough that could finally lead to a definitive detection. The existence of these streams does more than just aid detection. It provides a unique laboratory for studying dark matter itself. By meticulously mapping the precise path and density of a stream like S1 using Gaia's stellar data, astronomers can perform a remarkable kind of cosmic autopsy. The way the stream has been stretched and distorted tells a detailed story about the shape and density of the Milky Way's dark matter halo that did the distorting. It acts as a gravitational probe, revealing the invisible structure that we cannot see directly. Furthermore, the very survival of these thin streams over billions of years places strict limits on the properties of dark matter. If dark matter were made of large, planet-sized objects or were prone to significant self-interactions, these delicate structures would have been shredded and scattered long ago. The fact that they remain so coherent and thin is yet more evidence that dark matter is likely composed of a sea of tiny, weakly interacting particles, just as the WIMP and axion models suggest. We are learning to read the history of the cosmos written in the motions of stars, a narrative that reveals the hidden architecture of the dark universe all around us. But if we are truly surrounded by a sea of invisible particles, why have our most sensitive detectors remained stubbornly silent for decades? To answer that, we need to consider the possibility that we've been searching for the wrong kind of ghost. What if dark matter isn't a completely new, undiscovered particle, but a strange, heavier version of something we already know exists? This brings us to one of the most intriguing ideas in modern physics, a potential bridge between the known and the unknown, the mysterious connection between dark matter and neutrinos. You are already intimately familiar with neutrinos, even if you don't realize it. Trillions of these ethereal particles are streaming through your body every second, emitted by the sun, from distant supernova, and even from the natural radioactivity in the Earth itself. They are the universe's ultimate ghosts, so notoriously reluctant to interact with normal matter that most will pass through entire planets without even a whisper of a collision. For a long time, they were actually thought to be massless, moving at the speed of light. But groundbreaking experiments in the late 1990s revealed something astonishing. Neutrinos do have a tiny amount of mass, and they can oscillate, spontaneously changing their identity between three different types as they travel. This discovery earned a Nobel Prize, but it also opened a Pandora's box of new questions. Their masses are perplexingly small, and the pattern of their oscillations suggests that our current standard model of particle physics is still incomplete. This is where a compelling and elegant hypothesis enters the stage, the sterile neutrino. Imagine our three known neutrino types, the electron, muon, and tau neutrinos, as actors on a stage, constantly interacting with the world of matter. The sterile neutrino is proposed to be a fourth, heavier sibling, but one that is a complete recluse. It would not feel the weak nuclear force at all, interacting only through gravity. This makes it, by definition, even more ghostly than its already elusive relatives. It is the perfect candidate for a dark matter particle. It would have been produced in the hot, dense conditions of the Big Bang in colossal numbers. Its sheer abundance and inherent darkness would allow it to form the gravitational scaffolding for galaxies without ever revealing itself through light or collisions. The beauty of this idea is how it could solve two massive puzzles with a single, elegant concept. For cosmologists, it provides a potential identity for the dark matter that shapes the cosmos. For particle physicists, it resolves the nagging anomalies in neutrino data. Some experiments have recorded curious bumps and inconsistencies in the way neutrinos oscillate, tiny statistical glitches that could be the first indirect hint that these sterile particles are real, subtly influencing their lighter cousins from the shadows. The sterile neutrino wouldn't just be dark matter, it would be the key to a more complete theory of the fundamental particles that make up our universe. The hunt for these phantom particles is underway in some of the most extreme environments on Earth. Deep underground, in abandoned mines and tunnels, physicists are not waiting for a sterile neutrino to come to them. They are creating its potential offspring. If a sterile neutrino exists, it could be slightly unstable. Theory suggests it might spontaneously decay into an ordinary, detectable neutrino and a burst of high-energy X-ray radiation. Teams are now using incredibly sensitive X-ray telescopes, both on satellites and in underground labs, to stare into the darkest places they can find, like the heart of our own galaxy, or the seemingly empty spaces between galaxies, searching for a faint monochromatic X-ray signal at a specific energy that has no other astrophysical explanation. It is the ultimate cosmic needle in a haystack search, looking for the faint death cry of a particle that may have helped give birth to the universe itself. Finding that single, specific X-ray line would be a discovery of monumental proportions, finally illuminating the dark and rewriting the rules of reality as we know them. For hundreds of millions of years after the Big Bang, the universe was a profoundly dark and simple place. It was an expansive, silent sea of neutral hydrogen gas, cooling in the expanding darkness, waiting for a spark. This epoch, known as the Cosmic Dark Ages, was the long, quiet pause between the brilliant flash of recombination and the dawn of the first starlight. Then, somewhere in the unimaginable blackness, a pocket of gas finally collapsed under its own gravity, grew dense and hot enough, and ignited. That first nuclear furnace was the birth of the very first star, a solitary beacon punching a hole in the pervasive darkness and heralding the end of the cosmic night. This moment, the cosmic dawn, was one of the most transformative periods in the history of the universe, and we are now beginning to understand that the invisible hand of dark matter may have been the chief architect of this revolution. The journey from that first star to a universe ablaze with galaxies is a process called reionization. Those pioneering stars were not like the Sun. They were behemoths, hundreds of times more massive, burning ferociously hot and blue and living short, violent lives. They flooded the cosmos with intense ultraviolet radiation, which began to strip electrons away from the neutral hydrogen atoms that filled intergalactic space, reionizing the gas and making the universe transparent to ultraviolet light once more. But this process didn't happen instantly or uniformly. It was a gradual, patchy lighting up of the cosmos, and the timing and pattern of this reionization are a critical record of how those first structures formed. For decades, the story seemed straightforward. The first stars did it all. But increasingly, cosmologists are uncovering clues that another, invisible power was at work behind the scenes, potentially providing an extra source of energy that either helped or hindered this cosmic transition. This is where dark matter enters the narrative of the cosmic dawn in a radical new way. We've long known that dark matter's gravity provided the scaffolding for the first galaxies. But what if its influence was more direct? What if dark matter wasn't just a passive anchor, but an active participant in heating the early universe? This idea centers on the possibility that dark matter particles, through their very nature, could have provided a significant and previously overlooked source of energy. If certain dark matter particles are their own antiparticles, then whenever two of them collide, they can annihilate, converting their mass directly into energy in the form of gamma rays, electrons, and other standard particles. Alternatively, if some dark matter is unstable, it could slowly decay over astronomical timescales, releasing a steady trickle of energy. In either scenario, this energy would have been injected into the primordial hydrogen gas, heating it up long before the first stars ever switched on. The implications of this are staggering. The formation of the first stars was a delicate balancing act between gravity, which pulls gas together, and gas pressure, which pushes back. Colder gas can collapse more easily to form stars. If dark matter annihilation or decay was actively heating the gas during the Dark Ages, it would have made it harder for the first stars to form, potentially delaying the cosmic dawn. Conversely, this extra energy could have had a more complex effect, perhaps preventing gas from collapsing into the very smallest dark matter halos, or even providing the final push needed to trigger collapse in certain regions. The key point is that this dark matter feedback would have left an indelible imprint on the entire reionization process, affecting when the first stars ignited, how brightly they shone, and how quickly they were able to tear apart the cosmic fog. How can we possibly probe such a distant and faint epoch to test these ideas? The answer lies in tuning our instruments to the universe's most ancient radio station. The primordial hydrogen gas that filled the dark ages emits a very specific radio signal at a wavelength of 21 centimeters. This faint whisper, stretched by the expansion of the universe to meters in length, is our only direct window into that time. By mapping the intensity and distribution of this 21-centimeter signal across the sky at different frequencies which correspond to different distances and thus different cosmic times, we can create a three-dimensional movie of the cosmic dawn and reionization. We can see the pockets of hydrogen gas as they are heated by the first starlight and watch as the bubbles of ionized plasma grow and eventually merge. This is the primary mission of a new generation of incredible radio telescopes, most notably the Square Kilometre Array, or SKA. Once fully built across sites in South Africa and Australia, the SKA will be the most sensitive radio observatory in history, a forest of antennae designed to hear the faintest echoes from the edge of time. It will map the 21-centimeter signal from the dark ages and reionization with breathtaking precision. If dark matter annihilation or decay was indeed heating the early universe, the SKA should see the evidence. The pattern of heating it detects won't match the pattern expected from starlight alone. There will be anomalous regions that are warmer than they should be, or a global signature of extra heating that began before the first galaxies could have possibly provided it. Finding such a signal would be a monumental breakthrough, offering our first direct glimpse into the non-gravitational physics of dark matter and revealing its role in one of the most important chapters of our cosmic story. We are on the verge of watching the universe turn on the lights, and we may soon discover that dark matter helped to flip the switch. We've arrived at the final and perhaps most mind-bending frontier of this entire cosmic mystery, a place where empirical science meets profound speculation. What if the inexplicable value of dark energy, that tiny, repulsive number that seems so finely tuned, isn't a puzzle to be solved within our universe, but a profound clue that our cosmos is just one page in an infinite book? This is the radical possibility that the answer lies not in our universe, but in the existence of the multiverse. The enigma is stark. For dark energy to allow galaxies to form and life to emerge, its value has to be within an incredibly narrow window. If it were significantly stronger, the universe would have blown itself apart before gravity could pull matter into galaxies, stars, and planets. A more powerful dark energy would have created a cold, empty, and eternal void. If it were much weaker or even attractive, gravity would have quickly reversed the expansion, causing a catastrophic big crunch that would have ended the cosmos long before life could ever get started. The value we observe is not just right, it seems improbably, almost suspiciously perfect for our existence. This apparent fine-tuning leads us directly to a powerful and controversial line of reasoning known as the anthropic principle. In its simplest form, it suggests that the physical constants of our universe must be compatible with the existence of observers who can measure them. We shouldn't be surprised to find ourselves in a universe that allows us to be here. It sounds almost like a tautology, but when combined with the multiverse concept, it transforms from a philosophical curiosity into a potential scientific explanation. This is where string theory, the leading candidate for a theory of everything, enters the stage with a breathtaking prediction. For decades, physicists hoped string theory would provide a unique set of equations that would predict all the constants of nature, including the value of the cosmological constant. Instead, the mathematics revealed something far more vast and bewildering, a landscape of possible solutions. Current estimates suggest string theory allows for a staggering 10 to the power of 500 different possible universes, each with its own unique set of physical laws and constants. In this view, dark energy isn't a fundamental, fixed number. It's more like a dial, and the dial can be set to almost any value across this unimaginably vast landscape of possibilities. Our universe, with its specific, life-permitting value, is just one possibility that was randomly selected when our particular bubble universe inflated into existence. This multiverse perspective reframes the dark energy problem entirely. There is no deeper reason within our universe for why the dark energy density is so small. Asking, why is it this number, is like a winner of the lottery asking, why did I win this specific lottery? The answer isn't found by studying the winner alone, but by understanding that millions of lottery tickets were sold, each with a different number, and it's statistically inevitable that someone would get the winning combination. In the cosmic lottery, a universe with our specific dark energy value is the winning ticket that allows for galaxies and life. In the unfathomably vast multiverse, with countless universes where the value is too high or too low, universes that are empty or have already collapsed, it is no surprise that we find ourselves in one of the rare habitable ones. Our presence as observers selectively filters the kind of universe we can possibly inhabit. This idea remains one of the most debated in all of modern physics. Critics argue it is ultimately untestable and therefore borders on metaphysics rather than science. If we can never observe these other universes, how can we possibly verify the claim? Proponents counter that the theory makes a statistical prediction that observed values of constants like dark energy should be typical of those found in habitable universes. Our measurements, which show a value that is small but not zero, fit neatly into this predicted range. Furthermore, they argue that the multiverse may eventually leave indirect fingerprints on our observable cosmos, perhaps imprinted in the pattern of the cosmic microwave background from collisions with other bubble universes in the distant past. While highly speculative, this keeps the door open for a future falsifiable test. Whether it is the final answer or a stepping stone to a deeper truth, the multiverse concept forces us to confront the profound and humbling possibility that the strange fitness of our universe for life might be the most important clue we have, pointing toward a reality so vast and strange that our cosmos is but a single, shimmering bubble in a frothing ocean of creation. And so we arrive at the end of our journey, having ventured through 30 of the most profound mysteries the cosmos has to offer. From the initial, perplexing observations of Fritz Zwicky to the shocking acceleration revealed by distant supernova, and from the ghostly halos enveloping galaxies to the cosmic voids expanding faster than the universe itself, we have explored a reality where the visible is merely the tip of a vast, invisible iceberg. This is not a story of completed knowledge, but a testament to the power of curiosity, a narrative that shows how every answered question inevitably unveils a deeper, more complex layer of the unknown. The journey to understand dark matter and dark energy has fundamentally upended our place in the cosmos, revealing that we are not made of the universe's primary substances, but are instead a rare and beautiful afterthought, a fleeting pattern in a sea of darkness. The true weight of these mysteries lies in their collective implication. Our current textbook understanding of physics, as powerful as it is, remains woefully incomplete. The standard model of particle physics has no candidate for dark matter. Einstein's theory of general relativity, while resurrected by the cosmological constant, buckles under the weight of the vacuum energy catastrophe. The stubborn discord of the Hubble tension and the bizarre diversity of galaxy behavior suggest that we are grazing against the edges of our knowledge, pressing up against the boundaries of a map that ends with the words, "Here be dragons." To solve these puzzles will require more than just a new particle or a tweaked equation. It demands a revolution on the scale of quantum mechanics. Relativity, a fundamental rewriting of the rules that govern space, time, and matter itself. We are on the precipice of a new physics, one that will likely transform our conception of reality as radically as the ideas that gave us black holes and the Big Bang. Yet, this is not a moment for despair, but for unparalleled excitement. We are living in a golden age of cosmological discovery, armed with tools of unimaginable power. The James Webb Space Telescope peers back to the era of the first galaxies, the Vera C. Rubin Observatory will map the cosmos in unprecedented detail, and the Euclid Space Telescope is already measuring the subtle distortions of dark matter and the accelerating push of dark energy with breathtaking precision. Deep underground, next-generation detectors continue their patient watch for a whisper from a WIMP or an axion, while radio astronomers tune into the faintest echoes from the cosmic dawn, listening for the hidden role of dark matter in the universe's first light. Each new experiment, each new observation, is a potential key that could unlock one of these 30 doors. This is why the story of the dark universe is ultimately a human story, a celebration of our relentless drive to look into the unknown and demand an answer. It is a saga built on the shoulders of visionaries who dared to trust the math over their eyes, who pursued anomalies others dismissed, and who built machines to sense the imperceptible. The next chapter is being written right now in laboratories and observatories around the world, and it belongs to all of us. Stay curious, stay engaged, and follow along as these cosmic detective stories unfold. For in the grand search to understand the darkness, we are not just mapping the hidden architecture of the cosmos. We are ultimately discovering what it means to be a conscious part of it, gifted with the reason and the wonder to even